Hello, everybody. My name is Umesh Kumar Parmar, and like everybody going to a restaurant, bar, and a club, and they order some cocktail and different kind of drinks. So you see there different kind of machine for making cocktails and drinks. So probably my question is can you make that kind of machine at home? Yes, you can. So today I'm gonna show you how to build that kind of machine at home. And my project is automated cocktail mixture. We're gonna cover this topic like cocktail mixture machine, different cocktails, different parts and their function, block diagram, schematic diagram, concept drawing, program installation device. So let's begin with cocktail mixture machine. So you uh, most of time like in marketplace you see that kind of machine is available you can see the drinks are top on the device and there is a little paddle uh, so you can easily select your cocktails from using that little paddle. Even that display help you for select any cocktail. Even you can make your own customize drink with the help of that little paddle and switches. So next is different cocktails. So probably for in my project, I'm using solenoid valve, which it's open. When it's open, that time drinks pour in the into the glass. So you for your drink, you probably you know about your ingredients and drink. So first of all, you have to you know about like measurement of your cocktail and almost all the ingredients and you can set the time for open and close that valve so you can make your perfect cocktail in your glass. So here you can use like orange juice, lemon juice, cranberry juice, even different kind of juice so you can make your own cocktail at home. Next one is the different parts and their functions. So let's begin with the first part. It's regulator IC LM7805, which convert 12 volt into 5 volt. So 12 volt supply for my solenoid valve, and it's convert into 5 volt, which going in my Atmega 32 8P microcontroller. Next one, it's Atmega 32 8P microcontroller IC. You can say it's brain of my device because it's control all the parts. Like it control solenoid valve for open and close. Even it's control display and IR sensor. So basically, it's my main part of this device. Next is IR sensor. So I'm using IR sensor for sense the glass at the placing area. So when you put the glass, you first of all you can see the message on the screen like place the glass in a placing area. So when you put the glass in placing area, it sends and it gives signal to Atmega, and Atmega do the further function. This is a transistor. I'm using IRF 520 transistor for as a switching because I cannot give 12 volt supply direct to the solenoid valve because, through the atmega. So I'm using a transistor for that. It need a 5 volt gate signal which get from atmega, and there is a second and third pin. It's drain and source. So probably I'm gonna connect my solenoid valve in a 12 volt supply. Second terminal connect to the drain, and source is to be ground. So when IR sensor when transistor get uh, gate voltage 5 volt, then it's become a switch turn on and turn off. Next one is solenoid valve. Solenoid valve is operate on 12 volt DC, and it's a one way valve. Even when it get 12 volt DC supply across the two terminal, it's normally closed, become normally open. So your drinks uh, flow through the solenoid valve. The display, I am using display for all the different messages. Even you can see the whole process of my device in the screen. Like when you start that device, that time you can see some message on the screen. Even like all the process, like put glass in a placing area, and after that you can select your cocktail. That kind of message you can see in the display. Next is concept drawing. So this is my front view. This is the side view. This is the top view. At front side, you can see these two are my IR sensor, and these all are push buttons. Four push buttons, four LEDs, and one LCD. It's mounted at front side, and this one is bottle holding area. So my all the drinks bottles it's holding here, and its height is 80 centimeter, and holding area height is 65 centimeters. This is my block diagram. I'm gonna tell you about my how my device is work. Uh, First of all, it get 12 volt DC supply through the adapter, and that 12 volt supply go through the like MOSFET to the solenoid valve, and that 12 volt convert into 5 volt with the help of LM7805 voltage regulator IC. Here, that dotted line it shows non-electrical logic flow, and first IR sensor sends the glass, and it gives a signal to at mega 32. After that you can see the message on the display. Like now you can select cocktails. So after that push, there is a four push button for different cocktails. So you can press any one switch. Then Atmega operate MOSFET for a specific time. So MOSFET controls solenoid valve. It's open solenoid valve and close the solenoid valve. That time when it's open, drinks pour into the glass. That LED is it's a indicator for uh, it's indicator for functioning of solenoid valve. When it's on, which solenoid valve it's open. It means like which drink right now it's pouring the into the glass. That time that LED is glow. Next one is my schematic diagram. So here you can see the jack pin. So let's start with the power unit. So this is my power unit. It's got a 12 volt supply to the adapter to the jack pin. After that, I connect to one switch, which help me turn on and turn off my device. After that, that 12 volt, it's convert into 5 volt through the LM7805 voltage regulator IC, and this 12 volt uh, supply I give it to solenoid valves, and here 5 volt give to atmega. After that, selecting area. So when uh, when you put the glass at placing area, IR sensor sense that glass at I set the value for IR sensor, so it gives analog signal to the atmega. After that, you can see in the display like now you can select the cocktails to so you have to push the buttons and it gives when that digital pin it's high, then it gives further process like it's open this solenoid valve for specific time with the help of IRF 520 transistor. I connect uh, fly diode for protection because it has a back voltage in when solenoid valve is open and when it closed that time it give back voltage. So I'm using flyback diode for that. This all LCDs, LEDs for indicator of functioning of solenoid valve. And here last is program installation. So I connect like 1 liter connector so I can connect my Arduino kit. I'm using Arduino kit as a programmer. Uh, no, it's like for installation device as an installation device. So I connect these 5 pins. One is 5, one is ground, one is reset, and RX and TX pin. So after that, I'm making my uh, a PCB layout in Eagle software, and I made this PCB in college and solder all the components on it. So after that, it's look like this. Next is flowchart. So it's when first of all it sees is there vessel is present. If it is no, then it show you that message again and again in the screen. After the when you put vessel in a place, then after it's show you the message on screen like you can select cocktails. When you select cocktails, that time that solenoid valve is open for specific time uh, and LED glow and that cocktail after that like finishing all the like process your in the last your cocktail will be ready in your glass. Here the code for my project. So So you can see I select 100 value for like it's an analog value which I show in Arduino program. So when I connect my IR sensor, then uh, I select the range for my glass area, and it show me like around 200. So I select 100 for that. It less than 100 when that placing area it's less than 100. It's analog value from IR sensor. Next is I this is like little example for one cocktails. Like when I press the push button number 3, then it become that pin become a high, and that solenoid valve is open for a particular time. So you can make your own. You have to just change this time for different cocktails, and you can build your own cocktail at home. So next is like Bun bootloader Atmega microcontroller. So we can't use directly Atmega IC on our board. We have to first of all Bun bootloader that IC. We have to connect our IC and fulfill this all the configuration with the Arduino kit, and go into the file and upload uh, a- at mega SIP file into the Arduino kit, and after that you can select the Bun bootloader. So your IC will be uh, Bun bootloader. So you can use for uh, installation any program. After that, you can use your Atomiga for like you can upload your any program in your that IC. So you need to remove this IC from your kit. After that, you can use Arduino kit as a installation device, and you have to connect the reset pin and TX, RX, and 5 volt and ground. So you can change anytime in your program. So you need 16 hertz crystal, 10K resistor, and 220 uh, 2 picofarad capacitor. So on the last, my project is look like that. So finally, you can build this device at home, and you can enjoy your cocktails at home with the help of like you need just this component, and build your own circuit, and may you can use this code for making different kind of cocktails, and you need to just change the time for different cocktails. This is my reference. Thank you. So I'm gonna do the my demonstration of my project. So here This is my whole project. You can see that? Can you see that?
Yeah, yes,
Yeah, we can see it.
Be nice if you could straighten it out a little bit.
Yeah.
There you go.
So right now you can see in the screen. So, like first of all, put. Can you see the screen?
No, it's too far. What does it say on it?
Okay. Maybe it's too little far.
Actually have two images on your screen.
It's a place glass.
Yeah. So
Okay.
when I put the glass,
What does it say, Umesh?
it says, which drink do you like it? Then when you so it's a drink. It's will be ready in one 1.5 minute. Yeah.
Umesh, now that it's kind of zoomed out, can you aim the camera at the glass and just try it again? Press the button again.
Yeah, sure.
We can't see the glass though.
Mm,
That's good, thank you.
If you pull the glass out, does it stop pouring?
no, because no, it's not stop. I need to change in my program, so it's gonna be stop. Yeah. So you can ask me question.
Yep. So thank you for the presentation and the demonstration.
Thanks, Umesh.
Does anybody want to start?
If you got questions ready there, Dennis.
Could you bring up your schematic, please?
Sure.
So your schematic is version 1.3, which is the same as what I have here, but in my documents package. But I think there's differences. Definitely is differences in my schematic and yours. When I look at my schematic on the left-hand side, there's the jack pin symbology is different and so on. Could you explain that to me? Why you would have a schematic with two same version numbers, but they don't contain the same thing?
Because unfortunately I submit wrong schematic on that time. That's why. Like this is my right one, but that time.
Okay, I can understand that. I don't have a problem with you submitting a different schematic. I have a problem with the fact that these are two different schematics with the same revision number. Do you understand? Your schematic has revision number 1.3. Mine has 1.3. They even have the same date and everything. If I didn't have the two schematics to compare, I would not know that the two schematics are different, and therefore we might be having a conversation based on two different documents.
Okay. Sorry about that. Like that time I changed in my in schematic, and I saved that two file as a PDF. But unfortunately, I submit that file.
No, I understand you submitted, but what I'm pointing out is you need to, when you do changes, change your revision numbers too. Okay.
Yeah,
that's what version control is all about, and that's very important. Very, very important.
Sure.
Okay.
Like because of that, like first of all, I changed that. I had that different jack pin before, and after that, I did some changes, and like after that, I forgot.
And that's fine. That's fine. I've absolutely no problems with that at all. Just again,
I can understand.
That's why version numbers are there, so that
we have to change
understand that we're not on the same document, right?
Version number. Yeah.
Could you bring up your? I'll come back to this after, or maybe somebody else will. But could you bring up your flow chart, please?
Sure.
So in your flow chart, okay, I'm glad to see you did use a flow chart. Okay, we start from the top. We go start, right? A diamond means we make a decision, right? In programming, decisions are what? The outcome of a decision is either two conditions. Which ones?
Like, is there any vessel is available or not?
That's right. There's only two conditions, right? True or false, yes or no, 1 or 0, right? That's how a decision is processed, right? So in this case here, let's say, is the vessel present? Yes, right? So we go down another diamond here where we make a decision. Is the cocktail selected? No or yes. But my problem here is when you go to yes, you have two paths that come out here.
Yeah, like one.
So which one do I pick as I'm going through your flow here?
That both are start at the same time. Like
no, they don't. No, they don't. They do not start at the same time. If we go look at your program, I am sure they do not start at the same time. One starts before the other.
First of all, in display, it shows the name, and when solenoid valve is open, that time.
So which one happens first?
Display.
The display. So why are you showing them that they start at the same time here? Do you understand what I'm saying?
Yep. Yeah. I understand
This should be. In your case, after the decision diamond, you should have a block on the yes side. You should have a block that says LEDs glow and display the name of the drink. Then another block underneath that, particular valves are open, and mix the drink, and then we go to cocktail ready after that. Okay? Do you
Okay.
understand?
Yeah. Yes.
All right, that's very important. Right, that the flow here doesn't make sense. You guys are doing these parallel processes, which again, unless you're doing multi-threading, which none of these micros can do, unless you're doing multi-threading, that this makes no logical sense. All right,
Okay.
one process has to occur before another. Okay, and I'm
Sure.
sure if we go into your code, in fact, bring up your code in those sections there. Okay.
Yeah.
So show me where the decision making process is. What was it again?
Which one
So is the cocktail selected, right? You had that.
Yeah. Yes.
Okay, where is that in your code?
Like this one. When we push the buttons, like 3 number, then
Okay.
that pin is high. After
Okay.
that you can see the cocktail number 3 in the screen,
So there you go.
after that it shows like a first solenoid valve open for that specific time. Like I put 6,000.
Yep.
And after that it become a low. It means that solenoid valve is turned off. And after that second solenoid valve is open for a specific time, and it's low. So this is the process.
Okay. So again, I'll point out you use the word, the LCD displays this then the relays, right? So in other words, it's a linear sequential process. So if we go back to your flow diagram, that's not what's shown there, right? On your flow diagram, you're showing a split where things are happening supposedly at the same time, which is untrue. All right.
Okay. Yeah.
Okay. Anybody else have a?
Just a quick comment, perhaps, on the drawing package. In addition to having version issues, I guess, unfortunately, your code was not in the package. So that's not really a question. I'm just pointing out something that should have been considered when you submitted your drawing package.
Okay.
Can you go to the schematic again, please? If we look at U2, all right, the 7805 there, okay, it has 2 capacitors there, C1 and C2.
Yeah.
Okay, what are their what's their purpose?
The purpose, like I took that information from the website. So, like
which website?
Exactly from the component101.com.
Okay, and who is the author for component101.com? What's their background that you're basing your career on? Did you look up the 7805, the spec sheet for it?
Yeah.
So you looked it up, you read through the whole...
from DGKey, yep.
Okay, and you read through the whole thing, you understood the whole thing, you referenced it when you did your design? Because I wouldn't trust somebody else's design. I would want to know, I would want to make sure that everything that, just because people do things sometimes doesn't mean it's right. If you look
exactly, I don't know about that capacitor, like as a filter.
Okay, well, let's not worry about the capacitors for a second. By the way, the data sheet will tell you why those capacitors are there, what size they should be, okay, and what happens if you don't have them there. But the 7805, interestingly enough, the manufacturer of this, TI, I believe it is, okay, has some more suggestions for you as far as using their IC. The manufacturer actually suggests that there be a diode placed between pins 1 and 3 in reverse bias. Did you know that?
No.
No? Okay, you might want to go look at why, because without it, you run the risk of eventually possibly blowing up your 7805, making it fail. Okay. You can't, when you go look at these really light, I use that in quote, light maker sites, or sites for hobbyists and things like that, you have to take their information with a big grain of salt. Do you know what that means?
Yeah.
Yeah, you got to be like, it's a nice place to start, but I should look into this further, okay? And a lot of times where the correct information lies is in the specification, the data sheets, okay? The data sheets are from the manufacturer, and let's not forget the manufacturer wants you to use their product, and he wants you to buy their product again, and he wants you to buy 1 million of their products so that they can sell a lot of them. So they tend to give you the correct information, but they put out a product that is multifunctional or has 1,000,001 uses in that, and they will give you all the information, and those spec sheets end up being multi-pages because of that, and you have to go look at that and read the data sheet. You told me you looked at the data sheet, you read the data sheet, but yet you didn't see the fact that I'm sure there's a figure on there that has that reverse diode protector there. I'm sure of it, that it's there, and you didn't see that. So you should have questioned yourself. You should have said, why did the manufacturer tell me to put it there, but I don't know, whatever that website was, didn't bother doing that.
Okay.
All right, that's important. All right. Anyone else want to join in?
While we're on the schematic here, I see that there's a lot of components within the circuit that are powered by 5 volts, and then at the far right side, the control unit that's all powered by 12 volts. But where is the source of these voltage sources? I guess they're not indicated anywhere. Yeah, the 12 volt and the 5 volt used within your circuit. Where's the source of it?
I removed from the it's from here, but I didn't indicate here that 12 volt. So basically, it get it get a 12 volt supply from adapter, and that supply going from here to here.
It should really be documented.
Yeah.
So
I got another question too. Denis, are you done or?
No, go ahead.
I was just going to Mr. Broad here put out this question here. Your input buttons, PB1, PB2, PB3 there. Okay.
Yeah.
Mr. Broad has indicated that the way they are set up at that moment would not work. Can you tell me why they would not work as they are set up there on your schematic? I'm not saying that maybe functionally they obviously work, but on your schematic, what is wrong? If I press PB1, all right, what do you intend to happen on pin D5?
Oh, okay. Yeah, I need to connect that digital pin at bottom side with between the register and push button.
Yes, exactly. So I would say your schematic has an error, 4 errors, right?
Yeah.
Very good. Yeah. Because otherwise, what would the pin D5 see right now, no matter what happens to the button?
Yeah.
What would it see right now?
It's give directly supply to like 5 volt to the digital pin.
It'll always see 5 volts no
Yeah,
matter
it's
what the state of
already a
LED
high.
running.
Yeah,
That's right. And if I press the button, nothing will change, right? It'll
nothing's
still.
gonna be changed. Yeah.
That's right. Okay. Could I also ask you? I notice you have LED 1, LED 2, LED 3, and LED 4. You have a red, green, yellow, and blue button or LED.
Blue,
Okay.
yeah.
And you chose to use R4, R3, R2, and R1 as 220 ohms for each one of them. Okay. Do your LEDs light up at the same brightness?
Yes.
You're sure? You're sure? LED 1 is a red LED. LED 2 is a green LED.
Okay, yeah.
LED 3 is a yellow LED. Do they all have the same forward voltage drops? LED 4 is a blue LED. No. So therefore, if they don't all have the same force drop,
yeah.
How much current will be flowing through each one?
1 point for
especially the blue LED, which typically has a very high forge voltage drop, right?
Yeah.
So that means R1 has very little voltage across it. Therefore, the current that's going to go through it is going to be significantly less than the other ones, right? So it'll probably be dimmer. Now we have to consider our eyes too. Don't see light intensity at the same values too. Okay, but you probably just pick rule of thumb values, which is fine. But I know for me, I tend to on devices, I really hate it when there's 3 or 4 LEDs and maybe one of them is much brighter than the other one. It gets annoying, right? It's especially if it's a device that's using a relatively low light setting. So you should consider that. Okay.
Okay.
Anybody else? Don, Denis?
Not really, but to add on the LEDs, I remember while he was doing the demonstration on Friday, the blue LED was actually the brightest. It kind of blinded me when I saw it. So it was kind of the opposite effect.
Oh yeah.
Same idea.
Yeah, probably the intensity level are not for the same voltage conditions are not the same either, right? You got to remember that.
Yeah.
So yeah, so we talk about photometric versus I forget the other term there. Anyways, which photometric is what our eye sees, and the other one is what actually is being emitted, right? So how sensitive our eye is to it.
I think Ron has a question here.
Yeah, that's what I was looking there, just to make sure. Did you? What's the purpose of the integrated Zener? Zeners.
It's the diodes D1, D2, D3, and D4.
Yeah, they are for flyback voltage. Like when solenoid valve, it's when it's turned on. After it's turned off, that time circuit get back voltage. So all the circuit it will be reset. That's why we should use diode across the solenoid valve.
But are they in fact Zeners?
No, it's not Zener diode.
So I guess what's in question then, is that the correct symbol?
Well, to be honest, I don't think that actually means that there's a diode inside the device. It's the fact that there's a Zener effect due to the MOSFET configuration. And a lot of people think it means that there's an actual integrated diode. There's a dioding effect due to the MOSFET's construction. So it's indicated by that. Okay. All right. So if you're looking for that protection, the switching protection, that's actually not a good way to do it. Okay.
Yeah.
All right. I guess we're out of time. Thank you. You did a good job there, and we will now take a break. And come back, and Rohan will talk to us about his dual sump pump controller project that he has had to install in the field, and it had to work because it was requested from a potential customer. Maybe afterwards you can get some feedback from the customer too. All right, so we'll be back at 9:30 to continue with our presentations. Thank you, and thank you, Umesh, for your great presentation there.
Thank you.
Okay, welcome back. Sorry about that. Just a little delay on my part there. I wasn't sure if we were up again. All right. So next we are going to have a presentation by Mr. Rohan Bavsar regarding a dual sump pump controller project that he did. Rohan, are you ready? We don't have audio. Am I the only one that doesn't have audio here?
Yeah. Is it audible?
Yeah.
There you go.
There you go.
Okay. Yep. Perfect. And you can see my white screen, right?
Yes.
Okay. All right. So yeah. So basement are the not place for the swimming. It's look funny, but it's a big issue facing by the many householder in a countryside. Their basement got flooded at this level because when they sleep at the night and the pump doesn't work, in the morning they say the situation. So I'm making a dual sump pump controller, and as you know, my name is Rohan Bhavsar. I am a electronics engineering technology student in NBCC, and I did my bachelor's of engineering in electrical in India. My advisor is Ronald Broad, and for him I make this project. And if you scan this QR code, you can get the more detail about this project. So today I'm going to represent dual sump pump controller introduction. I'm going to show the conceptual drawing and the functionality for the project. Then I'm going to show the details about the block diagram. Then I will cover wiring diagram for my project. Then I'll show my part list, what components I use. And I show my enclosure design, how I take the measurement and how I design that. Then I will cover the PLC ladder logic. So for that, I will cover all the parts for the PLC ladder logic. So if you are not aware of that, if you are not familiar with the PLC, don't worry, I will start from scratch, and I'm considering some of the junior and some of the non-technical advisor, non-technical faculties are here. So I will start from scratch, and that will show some testing and the results which I did on my project. And at the end, I will conclude myself. So for the introduction, I say it's an issue brought up by my advisor. He is facing the issue is pump doesn't work efficiently, and his basement flooded by the water all the time. And so we decided to make this project, and instead of using the single mechanical float switch, we are introducing the two pumps. And we are not using this float switch. We are just tying them out, and we are just using the pump instead of the float switch. We are using the water levels. So in this project, I created the 3 water levels, which I will be covering in next slide. And you can see this is my front view of the panel, which have 4 indicators, like you can see the green light, 2 yellow lights, and 1 annunciator. I will tell you about the annunciator, and the 3 push buttons are there. And that's the right hand side view is from the view from the inside. So here is my conceptual drawing, and I can zoom here. So you can see this is a sump, and here I make my panel. So in this sump, you can see it's a 3 level of water I created. So first is a low level, high level, and critical high level. So these are all going for the PLC input, and it's attached to a different height. So low level is attached at the 4-inch of the sump, high level at around the 20 inches, and critical high is around the 23 inches of the sump, and the total height of the sump is 24 inch. So for the meanwhile, if you consider normal operation, when sump collecting the water start going on the this direction, and once it's reached to the high level, PLC allow to run the pump A. So at this moment, at the high level, pump A is running and trying to throw the water out from this pipe. And the meanwhile, it's if the water force amount of water is high, is more, and it's still going high, and if it is reached to this critical high level, pump B will be also join this operation. So at this critical high level, pump A plus pump B both working together and trying to remove the all water as they possible, as according to their capacity. Another thing is that if water remain above the critical high level for more than 2 minutes, and it's still going on or is stuck to the level, the annunciator, which is in front of the panel here, it start making noise and inform the user. And one more thing in the panel we can notice here, I haven't introduced the reset button, which you can see in this slide. It's here. So I will talk about that in further slides. So here is my block diagram. We can see here it's all the input signals are coming from the left hand side, and it's 7 inputs mentioned on the PLC. Oh, it's eight inputs, and there are 6 outputs on the right hand side mentioned. So in the meanwhile, we have a current sensors here, which protect the pumps from overload and underload conditions. So for example, my pumps are rated for a 6.7 ampere. That's the nominal load operation ampere. And I created the 2 brackets in the meanwhile. So if some of the circumstances have a pump running in the 5 ampere, or some of the condition in the block rotor, if it is some object come in the shaft and pump stop functioning, it's consuming around 9.2 ampere. So in the meanwhile, current sensor detect that and send the signal to the PLC, and PLC stop this contactor, which is mentioned here. Also about these 2 test pump buttons. So I introduced this test 2 button because it's not affecting any PLC logic. It's directly connected to the pump. So in other words, I can say it's bypassing the PLC logic. So in case your PLC doesn't work, and if you want to remove the water, or if you want to check the pump in that case, so it still work. Here is my indicators. So pump A and pump B indicators. So why I mentioned the indicator? Because it's the same indicator like LED bulb, and it's showing the 3 situation. So like if it is a there is a off mode, on mode, and if there is a fault, it's same LED start flashing for the pump A and pump B. And here is the system indicator. It's online, which I showed you earlier. It shows that the PLC is working all right. One more thing, it's annunciator. Yeah. So annunciator, like I give the name annunciator because it's a buzzer and the light both together. It's making noise and flashing light at the time. and it's informed the user about this critical situation. So that's why they keep the name annunciator here. And we can see here in the block diagram, it's a reset button. So this reset button introduced in the circuit later on for two main reasons. To stop this annunciator. So imagine if you see this situation, annunciator start, but once you go in the basement and yeah, now it's time to stop the annunciator. So that's why we introduced this reset button. If you press this reset button for 5 seconds, so it will turn off this annunciator. And another thing is when we are testing with this current sensor, so when the current sensor is let's see, I put the bracket of 5 ampere to the 7 ampere, and when they sense the 8 ampere, they send the signal to the PLC, and PLC turn off the load. But in the meanwhile, after the next moment, PLC sensing that there is no load, like there is 0 ampere going, because we already shut down the pump, so there is no load for that. So in the meanwhile, PLC sense that there is a nominal load again, it's a normal load, so start again. So like considering the cycle going continuously, so load is like load is on and off, on off, on off. This cycle is going continuously. So that's why I introduced this reset button. If you if there is a fault, it's start flashing on the panel, and once you press this reset button for a moment, it's resetting the load and it's scanning again. So once you press this, PLC scan if there is a clear fault is clear or not, and it's in the bracket or not. So that's all about the block diagram. And oh yeah, also yeah, I keep this 3 fuse here in my circuit for extra protection. So these 2 fuse which I'm mentioning here, it's rated of 10 amps, and this one is 20 amps is going into the whole system, and this one protecting the individual pumps. So let's move to the wiring diagram. So here is my wiring diagram. Yes, I use the different colors to show the input and output signals, and I mention in this left hand corner here. So here the black is a hot wire. It is, you can see it's come from the outside, it's a line. The orange is neutral, and green is a ground, which is goes to the PLC. And the output of the PLC, you can see here, it's a DC sensor supply. So I made the yellow here, and I made the silver contactor here. So it's easy to observe the wiring flow and the connections. And we can see here, I put the all indicator on this side, and this is my current sensor, this portion. I can show you the full figure of this current sensor later on. But you can see one thing from this contactor. So you can take this power supply, it's going in the 10 amp fuse I showed you before. And from the 10 amp, it's going in the contactor here. And from the contactor, it's going in an individual current sensor. So there is a 2 current sensor for each pump. So I use 4 current sensor in this circuit, and each protecting from overload and underload. They are making the bracket. So that's all about the wiring diagram. And oh yeah, one more thing. And this is going for the pump A and pump B. This is the supply going for that. So I'll show you my part list, and here is my part list. I use these parts, and I'm only considering the amount which I exactly used in this project. And you can see here is my cost is $1,239 to making this whole project. And most of the components I order from the automationdirect.com. Component and wide range of varieties of sensors and they have more components available on their websites. In the meanwhile, I can show you the current sensor. So current sensor, what I use is like it's working as a current transformer in the AC system. So you're passing the, can zoom it here. So we are passing the load current like the hot wire from this hole, and we are connecting the PLC inputs here. So consider like I can say that it's working as a relay. So I attach my PLC input here in this two terminal, and here is the, you can see the adjust point, and there is one LED light which show the status of this sensor. So if they detect the uh, in case I set the range of 10 amp, and when the load is above 10 amp, so when they detect, it's cut the supply from here, because the sensor I use is normally closed, so supply is going all the time. But when they trip or they trigger, they cut the sensors and they send this signal to PLC. So that's the normally close ampere, and it's a pretty big range. You can see it's 1 ampere to 150 ampere range, so can use in many applications here. Then I'm going to show my enclosure design now. So here is my enclosure design. So yeah, it's my logbook photo is all the detail I mentioned here. And here is a dimension I took that. So I just took the measurement from this website which I order, Automation Direct, and then I divided into the according to the parts, and the I start from the center here. Yep, I start from the center, and then I divide the all the components, and then I make it neat and clean that. And I use the unibit hole because I remember my LED light have a 22 millimeter diameter. So for doing this big amount of drill, I use the unibit drill, which is available in the labs. Then I will talk about my PLC and the ladder logic. So as we can see here, I put this details here because it's hard to find on the Siemens website. I use this Siemens PLC. You can see, you can search about that if you want to. It's a S7200, and which is unfortunately not available right now in the market. The company collect all the data, like there is no data available on the website. So I requested the one of the employee, like one of the worker, one of the guy working in the Siemens, and he provided me this data sheet, and he gave me the user manual, so I can learn the codes, ladder logic from there, because it's a different ladder logic from the one we learn in the classes from the Rockwell Automation. So before I start my ladder logic, I would like to share some of the points so everybody can understand the ladder logic. Even I'm considering the juniors are watching this video, as I say. So in the ladder logic, like you can use this bit. So we can say it's examine. If you put this instruction, these are the instruction, and they come up in the ladder logic. This is the flowchart, and this is the STL format. Is a three different type of ladder logic, like three different type of style of programming provided by the Siemens, and I'm using this ladder logic. So in the ladder logic, if you use this first instruction, it is called the examine if close. So it's check for the input. Usually it used for the input side. You can see standard inputs are here. So it's check whether the input is a close or open. Same thing for the second instruction. It is called examine if open. So this check the input is open or close. Here I can see it's a coil. It's usually go for output. So in my case, this is my contactor. This is my LED. This is my all indicators are here, and my all the inputs, like for example reset button, the current sensors, and yeah, remaining inputs are the XIC or XIO instruction, and all my outputs are the call instruction. You can see here. Then I'm going to show the timer instruction, because I use the timer instruction, like I use the 8 timer instruction in my project. So let me zoom it. So this is the block instruction. You have multiple inputs you have to put there, and you can see here input and output the inputs. So choose the input from here. You say the resolution, and it's give the maximum value, and we can use this number. So I can show you the actual instruction I use, and I will show the calculation for that in my actual programming. This is my first program which I perform in Windows 98. Yeah, I forgot to it to run this operation, like to run this program. You can see the step 7 micro Win32. This is the PLC Siemens software. So to run this, we need a Windows 98, and to do that, I install the virtual Oracle virtual machine, and I install this Windows 98, and then I install this program. And the in the meanwhile, we also suffering from the issue, like I don't have a DB9 cable in my laptop, so I order the serial port to the USB. Then I install the softwares and drivers, and it's a long process we did on that, and finally that's work later on. And next slide, we can see. So that's how in Siemens work. We have to define all the instruction before we using. It's not like in Alan Bradley. We can't we can't make the comments later on. We have to define all the instruction before. So like I define all my outputs here, and I just give the name according to that. And here is my all inputs. You can see I02, I7. So we have to define that first. And one more thing, instead of O0.0 in the Allen Bradley, it's a Q for the output. Siemens have a different way of writing the code. And let's begin with my ladder logic. So here you can see it's my ladder logic. I'm putting here. So from the network 1, network 2, it's all commented. Here you can see I use this timer instruction, and up to network 1 to network 5 here, it's all for the pump A. So we can see here it's a current sensor input here, and this is the disable the annunciator. So like it's a reset button here I'm putting. Next slide. Yeah, here is a main program, like he's a contactor for pump A, as I say, call instruction. So once it's reached to the high level, so it turn on the, and also we need a low level in this signal. I can zoom here. Yeah, it's a high level plus low level. So we need both of this, and one of the instruction I have put it for the 5-second delay. So we all need to be true, and then contactor A will be start for the pump A. It's the same scenario for the pump B, but it's one more instruction, like there is no high level, it's only working for the critical high level, which I will show you next slide. But before we move to the next slide, I can show you this program. You can see the network 6, 7, and 8. This whole program to blink the LED light. So it's not same as the Allen Bradley. In Allen Bradley, we are using the status bit, so we can use the S4 instruction to blink the LED. But here it's like we have to use the timer, and then we have to zoom here. Then we have to use this maths instruction here, and then we have to reset that again. So we are making the loop actually by the timer cycle. Once it's done, it's going from 0. So that's how the I blink the LED during the fault. And here is the starting of the pump B programming. You can see here, it's all the current sensor for that. And this is the reset button. It's the same as the A. And then it start here. Yeah, here is the logic for the contactor B. So yeah, you can see it's we need a critical high level, low level, and then going to be pump B will be turned on. So consider like we water is going from low to high and high to critical high, and in some of the case somebody or some issue happen and only critical high level turn on. Contactor B will be not going to be energized, and we need all this input, and then going to be contactor B will be turned on. One more thing I would like to mention here is like you can see the online indicator which I mentioned earlier in my front panel. So in the Siemens PLC, we cannot use this coil instruction only. So like for example, in Allen Bradley, we are using this coil instruction without any input instruction. It works, but not here. So I use this beat instruction here, M0.0, and it's normally it's examine if close. So it's always close when you get the supply. This indicator is on. In the next slide, I can say. So this is the logic for my annunciator. You can see it's the timer. You can see critical high level is. So once it's turned on, and yeah, here is the timer like 1200. So it's working the second. And for the T37, it's a multiplication of 100 millisecond. So it's a 2-minute timer here I use for the critical situation. And moving to the next slide. So yeah, I performed some of the testing on my project. So first I performed the current sensor calibration test, which is to make sure the load is under the bracket. Like as I say, my current rating is 6.7 amp, and I make that bracket by using this test. Another test I use is a for reset functionality test. I use the stopwatch and external water tank. You can see here, and I use the ammeter. We check the critical situation and reset the load by pressing the 5 seconds. In the conclusion, I can say this capital cost is more for this project, but in the meanwhile, once it's running, it's very cheap. Like you don't have to replace the pump, and it's save a lot of money. There is a really real fault. It's system connected to the PLC. PLCs are always accurate. It's functioning all the time. It's a user friendly. It's easy to change the pump, and anybody can use it using the uh, user manual, like my report. Protection, as I say, it's multiple protection on that. So there are fuse and current sensors are there to protect from all the circumstance. And the last thing I learned a lot of things from by making this project, and using the different PLC. It's really a great experience for myself. And yep, that's it for my presentation. Now I'm going to show the video for my demonstration. Is it audible?
There is no sound.
No.
No sound? Detail, you just scan this QR code. You can see this. I think now okay, right? On after the plugin, it's online.
Yes.
Yeah, we hear.
Sounds yeah. So let's see. It says that PLC is on and it's working safely. Another thing I'm showing is that's inside view, and if you want more detail, you just scan this QR code and they give you the more detail about. So now I'm going to show the normal operation. In the normal operation, water is going to fill by low level to high level to critical high level, and then we get the fall down the water again. So critical high level to high level and high to low level. So I'm going to turn on this external water tank, and I'm creating the artificial grain so we get some water in this sump. So let's see here, it's low level here at the bottom. This is the high level, and this is the critical high level. Once the water goes to the high level, turn on. And I'm putting some water with the mop bucket. I'm creating the flood here. The pumping is on right now. You can see pumping is on. It starts doing functioning. You can see here, it's pumping is on at the high level. Right now I'm creating the critical high level water with the help of this bucket. You can see water is up to here. These pumps are trying to send the water outside at this moment. And I'm going to stop the flow of water. So right now water level is below the high level and it's going down. Pump is working at this moment only, and you can see it's a low level, and you can see pump is stopped below the low level. We create the low level because we want to keep the pumps in the water all the time to prevent the dry run condition. So low level prevent from the dry run condition. So it's a critical high level, and I'm start my timer. So you can wait for 2 minutes to create the critical high situation. I put the timer here for the 2 minutes. If it is water going high above the critical high level, so you can see here that's the critical high level. This will inform the user by the annunciator. Wait for the 2 minutes for that. So it's almost 2 minutes here. You can wait for the 2 minutes, and annunciator will be stopped at 2 minutes. Yeah, you can see it start making noise. It's to inform the user, but once the user should inform, you want to turn off that annunciator. So that's why I put this reset button here. So press hold for the 5 seconds to turn off the annunciator. And now it's off. So yeah, questions?
Um,
Yeah, I'm
All
running
right.
about the time, so I close that video.
Yeah,
I'm
no,
running
that's
about the
fine.
time.
That's fine. You go with what needs to be done under situation. Very good presentation. Very good demonstration. Yep. Obviously, pointing out that it would have been impossible for us to see on site, right? Unless
you can take the appointment of Mr. Broad and you can visit that place.
Exactly. I guess my question is similar to a question we had yesterday. Is what's the difference between sound and noise?
Okay, sound is like the actual sound you are listening to my voice right now, but the noise is like I'm making this. It's noise. Again, we don't need in this sound actually.
Does your alarm make a noise or does it make a sound?
Sound.
It makes a sound. Okay, you use the term noise. All right, I think in the demo there. So okay, yeah. I mean, there is a distinct difference, right? Sound is something we desire to do. Noise is typically considered something undesirable.
Undesirable, right?
Yeah, exactly. All right. Denis, Don, Ron, did you guys have questions?
Well, I had a question. For the concept drawing, why did you use a hand-drawn drawing instead of a AutoCAD drawing?
Yeah, definitely. It's during that time, like all the instructor advised to like whatever your advisor describe, like whatever advisor say, do that. So my advisor said make the handwritten drawing, so I made that.
Okay, but I think that when you know you're going to do presentations and that, you should obviously resort then to technical drawings, right? I mean, it's the same thing as you used your logbook entries at one point,
Yep.
Those are informal documents typically. Anything that's hand drawn is considered an informal document that you and your advisor may be, trying to put down some information or whatever. But then when you're going to do some presenting to people or formalizing, your design, you have to go to a formal technical drawing.
Yeah,
okay.
Definitely. Definitely. I'm agree.
Yeah, I think your wiring diagrams and things like that were really, really great. But then, countered with the hand drawn, and it's not just that you showed it; you spent a fair amount of time on it. I don't know if Mr. Legier agrees with me with that, but if you would have just shown it as here's my initial ID, boom, okay. But to have spent a lot of time, and I'm sure you spent, I don't know, I really didn't time there, but
it's actually like
5 minutes or so.
Conceptual drawing and functionality together. So I'm showing the functionality.
So you should have had a better drawing.
Another drawing, yeah, you are right. Yeah, I can use that. That's fine.
Anything else, Mr. Legier?
Not really. That's the thing that stood out the most to me.
Don, I have a question for you.
Yes, please.
Good presentation, by the way. Enjoyed it.
Oh, thank you.
I think, and it's just a point of understanding, I think, clarification. I think I heard you say that you have overcurrent protection on both your motors.
Yep.
So if there were a blockage, for example, and your motor was to begin to overheat, overcurrent situation, it sounds your annunciator, it stops the motor, stops the pump?
No. So the annunciator is only for the critical situation. So if water is going high above the critical high level, it informs the user. But if the it is going above current, like as you say 11 amp or something, I already set the tripping point for 9 amp. So they send signal to the contactor, and the contactor signal sent to PLC, and PLC turn off the contactor. And in the meanwhile, it show the indicator of the fault. So start flashing the light.
The pump doesn't stop?
Pump stop, yeah. Contactor stop, yeah.
But it will continuously try to reset? You created a loop so that it would pause for an interval?
No, in the last term. Last term, we are performing that when we don't have introduced the reset button.
Okay.
That's why I introduced the reset button. So it's a kind of user interference. So you come to downstairs, you go to the basement, and you know, okay, there is a fault. Let me clear the fault, and then you press the reset button. So then it's continue.
Okay, that makes more sense. I
Yeah.
was confused. It
No,
doesn't
everybody, I
automatically
think
start.
everybody know in my class, like classmate know that I'm practicing with light bulbs, and light bulbs are flickering in the lab.
Yeah.
So everybody's observing that, and everybody know that flickering issue.
Sorry, I missed it.
Oh
Can
no.
I just add, maybe
Yeah.
I need a bit more clarification.
Yeah.
So just out of curiosity, if there's a overcurrent
Okay.
condition, the alarm doesn't sound, but the lights blink, and the user needs to go down and reset. Well, obviously clear the fault and reset the panel. Is that what it is, or?
Yeah, I can show you my front panel again.
But I'm just curious. Does the
Okay.
alarm, does the sound alarm sound also, or it doesn't?
Only start flashing, because you can see here it's two different indicator. One of for individual, so pump A and pump B. So here, yeah, you can see. So annunciator at the end. So it doesn't related with the annunciator. So if there is a fault, the only thing is pump A and pump B indicator start flashing. It's not making any sound.
So my issue, not my issue, but my advice to you is, for example, in my house, if I had that in my basement and something faults, and I don't notice it, okay. So yes, your device goes into a protective mode, which is great. But what happens as the water keeps coming in, and I don't notice there's a fault at that point, right? I don't go down and take a look, because that's actually happened to me before, where I thought I had something operating downstairs and it wasn't, and then when the calamity happened, that's when I discovered there was a fault. Okay, so I'm just saying that I think you need more than maybe flashing lights, because not necessarily everybody goes downstairs. For example, for me downstairs, I haven't gone for a few days to my downstairs because I didn't need to go get something down there. So if I had your system, it could actually be a couple of days before something happens. And whenever it rains, I don't want to have to run downstairs to take a look, or in the middle of the rainstorm or whatever it is, I don't want to have to go down anyways and discover that, hey, there's been a fault for the last 2 hours and the water's coming in anyways, right? I'm just, saying that maybe the audible alarm has some qualities to it that a visible alarm doesn't have in a system like this, because I don't think that panel, wherever you install this, more likely that panel will not be in a necessarily visible location all the time, right?
No, it's in the basement. Yeah, you are right. Yeah, I agree with your concern, but issue is that if in case pump A is not working, so it start flashing and water is going high at that way, right? Because pump A is not working. So in the meanwhile, if it is touched the critical high level, pump B will be turned on. And in case both pumps are fail, then it's go to the critical situation, the annunciator. So we cover your concern in this project.
Okay, that's fine. That's a good answer if that's what's happening, by all means.
May I comment too, or can you hear me?
Sure, yeah.
Yes, please.
Welcome aboard, Mr. Broad.
Okay, yeah. So I found a way not to get feedback with all the devices that are running here. I just want to comment too, if I could. Rohan worked very closely with me on this project, and this exact topic was discussed in great detail. Good. And so I think we had quite a few 1 hour sessions talking about how this should work, and I don't want this to be a nuisance that it's beeping all the time, like just because remember, it is a dual pump controller. So even if one pump has an issue, there's still a second pump there that can run. And all I wanted to be alerted of was if I had an extreme high water level, so that I could then go down and do something about it.
Okay. No, that's what my concern was there a way to
Yeah, we thought about this, and I just didn't want to be woken up in the middle of the night by a beeping sound, or actually, it was more my wife probably.
Yeah, that's what I say. I make this
Yeah.
project according to the user
Unless it's
requirement.
absolutely critical that I go down and check on it, right? So, otherwise, I want to throw the project out the window, right, Ron?
No, that's
Yeah,
I say.
anyway.
That's I make for the according to the user requirement, right?
Yeah. So anyway, I think there's lots of other questions we could ask, but I think we're out of time. So
Yeah, I stop my demonstration as well. So
yeah, I noticed.
yeah.
Yeah, it turned out good though.
No, I already sent you guys link for the YouTube.
I think Mr. Metcalf has frozen.
Yeah.
So thank you to Rohan for that presentation.
Yeah.
And we will take our a little bit less than 15-minute break, and and then who's next on the schedule there?
It is we have Cedric Nusti.
Oh, so we have
presenting
Cedric,
his musical band Mixer at 10:30.
All right.
Very
So
good.
we'll
Thank you, Rohan.
we'll
Yeah,
take our
thank
break
you.
and
Guys,
we'll
have a great day.
see Cedric at 10:30.
Sounds good.
Okay, Rohan, thank you.
Thanks, Rohan.
Welcome back, Dennis.
Oh, sorry. Yeah, I guess my my internet connection dropped here because my wife was having the same connectivity issues for her work. Sorry all about that.
Mr. Broad just opened up the break time. We'll be back at 10:30.
Excellent. Sorry about that. Okay, we're back. I'm sorry for me dropping out there. I guess I had localized internet problems, although I think some of the other students also indicated they had a bit of a issue. So anyway, my apologies for that. Excuse me. So back from the break, and we are going to hear about a musical band mixer with color organ project presented by Cedric Nishuti. So Cedric, are you ready to go?
Oh yeah, I am. Sorry about that.
All right, no, that's all right. So the floor is yours.
Okay. Yeah, okay. So thank you for that time. All right. Okay. Hi, my name is Cedric, and I'm so excited to be here with you guys to share about. Sorry, I would like you to share the screen first. I don't know if that would be possible. Just give me a second here. Trying to figure out. Can you guys see my screen?
Yes.
Oh, okay, okay. All right. Okay. Okay. Yeah. So my name is Cedric Chuti, and I'm so excited to share with you the idea about this project on which is a musical band mixer with a car organ. So I'm a student at NBCC in electrical engineering technology, and my advisor to this project was Mr. Dennis Leisure. So when I was in high school, I used to be a kind of like a guy who to do something about like a DJ, and I used to be like a master of ceremony, so that's where came the idea about like the music mixer, so that I can do by myself. Maybe if I have an opportunity like to travel anywhere with my friends, or I can do it or something. So yeah. Then, well, what are we going to see in this project? So those are the questions I asked myself, like what it is, like what is the project, how does it work, what does it do, and problem and the solution. The next slide would be about like the component used to build to make this project. Of course, there were the resistors, as you can see here. There's some resistors, capacitors, as seen here. Audio jack will be this guy right here. Power jack, that one right here. Then potentiometer, which will be that one, and diode. Sorry to forget, I had to mention which that one. This is your operation amps. So it would be LM3900. And yeah, so what is the project? Like what is the musical band mixer with the car organ? So this is the concept drawing. As you can see here, this is where the knobs are for the volume, where you will control your voice. If you want it a little bit higher, if you want low, if you want it a medium. So that's where you kind of control everything. So it would be up here the LEDs. The LEDs here, they're used to show the high frequency, low, and medium. So high, low, and medium. The green LEDs make sure they used to here to measure to show how higher is the sound. Then the red LEDs, they use they are kind of like a medium. They show the medium of the frequency of the sound frequency, and the yellow would be the low. So basically, that would be the side view on how it looks like. And and then on back view, we found the switch which is used to control the circuit, and the power jack will be around right here. So where you connect your the power source, so that you can get like the current to power your device or my device. And here we found like output channels. So output channels here, I've used in this one, I used 4 channels. In case you have multiple, like if you have more, like output, like to display those audio sounds. So that's why we have, if you have like more like speakers, so that's why we connect those speakers. And the input channels, that's where you will connect like if you have, for example, the laptop, if you have a microphone, if you have a telephone or whatever you want to plug on it, so that you will get the output on the speaker. Basically, that's what used. And those are the dimensions like between like the LEDs here. So basically, that's how it looks like. Then on the next slide, how does it work? So of course, this device will need like a power so that it can allow like to provide like the output. So for this time, I used like an adapter, like this AC/DC power adapter of 9 volt. I chose the 9 volt. Why? I chose the 9 volt because for the LEDs, those LEDs, they need like a 9 volt, and the IC amp I used, the operation amplifier I used, it can operate between 5 to 36 volt. So that's why I came up with the idea of using, okay, the 9. If I need a 9 for the LEDs, then I will use that one. So which is fine to the operation amplifier too. And then I use the switch that we control. I will use to turn on and turn off the circuit, or maybe the device. Then here we found something which is a input channel. As I said, like 4 inputs, the audio jack. So this audio jack we allow, that's where you will plug anything from the external device. So we have like our connector. Then our connector will be connecting like the external device, and will be connected to the external device and this mixer. And from that, we find the operation amplifier. This operation amplifier is used to amplify, or maybe to try to deliver. It will be used to deliver the data, the signals from the external device, and to display them on the output device. On that time, that's where you will find the LEDs, the filters here. It's connected to the input audio jack. That's where I need to know like how high, how low, how mid, like how is it the frequency of the sound I'm getting. So then those will be displayed. Sorry about that. Those will be displayed on that will be appeared on those LEDs. Where the green LED, they will demonstrate the how higher is. The red LED, they will be demonstrating the medium, and the yellow will be showing the low frequency. And then here you will find like a four input channels. So this one, that's where you will connect your connectors to the output devices, where I mentioned the speakers. So yeah, then in order to get in order to have your output, your audio or maybe anything you want to display out. On here, how does it work? Here I'm going to try to demonstrate and to explain how everything is worked inside. Who would like to to know what's going on inside of the mixer, how is it work? Then here we find, basically, as I say, I have 4 channels, and those 4 channels, they kind of operate the same. So that would be the first channel. the input, first input, second input, input 1, input 2, input 3, and input 4. So for the input, they can, because they are all the same, they can operate at the same. So I'm going to try to demonstrate, to explain maybe on just one, because they pretty much do the same thing. For the, when you get your input, when you connect your output, your external device, for example, mine right now, I can say like using the laptop, you will take a connector and connect your external to this input to input jack. Then the potentiometer used here would be the how, if you want like a low, if you want like a little bit higher, if you want, it's like to regulate your volume, like the sound you want to hear. Then it will be the capacitor used. Capacitor used here, it's kind of like it's trying to couple the AC signals and blocking the DC signals, because we're talking about here, we're talking about like this sound, or maybe it's the way to transfer the signals, the audio signals. So we need the AC signals, but we don't need like the DC signals. Then that one will be goes to the out to the negative input, to the negative of the audio of AC amp. Then here we have like this 1M, the resistor, for example, this one R32. That's where this one we allow, that's where you connect like, cause like, as I said, the operation amp, we need the voltage. We need like the current flow to allow it. So that's why we connect this resistor in it. And then this R25 and R33, they are used in order to allow like those kind of amount of the signals you want to, in order to get to this to the audio, to the output. And the capacitor 15 here, it will do pretty much the same thing as that one here. It's to allow to couple the AC signals by blocking the DC signals. Then on that one, for the input, for this input jack, where I will connect like the audio, the input audio jack, you will connect, because I need to display my LEDs to show the frequency, how they got how higher, how is the sound going by displaying it. So that's why you connect I connect my LED from, which will be these are resistor used right here. Those are resistor, they allow the current to flow. They kind of help the current to flow. This capacitor right here would be used this to allow those signals. If they need like if I need more, so they will try to allow the amount of current to flow. Then right here on this point, we found this transistor used, it's a 2N3904. So that one used, this capacitor is connected to the base of the transistor, and it will be with this resistor. So this resistor and that one, those one, they kind of allow those signals going through the transistors. And the diode used right here, the diode used will be in case there is a short current occur in the system, maybe to this, it will protect this transistor right there. Then, as you can see here, maybe they have different values, but they kind of do the same thing. Because like this one, like this low right here, sorry about that, my mouse is too touchy, it's kind of touchy. So when this section right here, this section, it shows that's where your high frequency, that one shows like the high frequency. And that one in the middle here show the medium frequency, and that one will be showing low frequency on how the tune, like the audio is sounding, like how is it. Then I used like 4 LEDs. I used the 4 LEDs in order to make it like a clear. You can use the 2, but I choose to use the 4 LEDs to demonstrate. For that one, because that's a green LED, those are the green LEDs. Excuse me. Those ones, you can choose the amount of resistor you want to use that one. It doesn't really matter that much, but remember, you have to know like the forward voltage of the LEDs. That's why you have to choose it. You may choose maybe being used like maybe like 200 ohms, but it would be better to know. So for my LEDs, the one I used, because those ones, they will be green LEDs. So I choose the 100 because that's the way I can get like which one is clear. I can get a clear output. And this, so I used like for the transistor I use this 2N3906. So which would be like those 3 transistors, they are all the same kinds, pretty much. So the high frequency will be displayed on this section, the medium frequency will be displayed on that section, and the low will be displayed on that section. Here we are going to see the problems accounted in this project and the solution. So as you can see here on my block diagram, that would be something seems like can short the whatever going like here I'm talking about like the signals, the audio signals. So if all the input channels are connected together, they will make like you won't have the ability to control. If you want to high, like if you wanted to increase the volume you want to hear, you won't do anything. So it will stay the same. So that's why I choose I choose to take like the potentiometer here. I try to open one of the channel here so that I can allow. Maybe this is the problem I was not expecting, but so far right now, that's how I try to solve that problem so that I can try to display and still see like the output I was looking for. Then by conclusion, that's how my device looks like. That's how like it should. As here on the top, right here you will find like the LEDs. So will be the yellow here. We show as I mentioned, the yellow here will be showing like the low frequency. The red will be showing the medium frequency, and the green here they will be showing the high frequency. As you can see here, that's where the switch on. This is the back side, like the back view. That's the switch. That's where you will control if you want to turn on and turn off your device. The power, that's where you will plug your adapter. And here you will see the 4 channels, the audio output channels. That's where you will plug them. For that one, that's where if you want to have like you can plug your speaker to that one, and it doesn't really matter how many inputs you have, the input device you want. So you will get like a single output for that one, and that's where you will connect your input devices so that you can get something to be displayed on the speaker there. And that's how like its top view how it looks like. So as I said, like that's the volume where you will try to regulate the how high you want, and those are the LEDs that will be displaying on outside, like to know like how high. If you want to reduce, or if you want to know like to see how higher your audio is being played. Yeah. Okay. Then that was the beautiful moment to share with you guys and the idea on how this project was made and built. So I'm going to demonstrate how this how I to demonstrate everything how it works right now. So just give me a second here. I'm gonna go back right here. Can you guys still hear me or see me?
In stereo.
Yes, we can. Yeah.
Okay, thank you so much. Thank you. So just give me a second right here. All right. Okay. Maybe that could be better. So now my device is on. So now I need to operate to try to do the display. So now as you can see here, that's where I need to plug where the input connector, where I will connect my own input. For this time, I will use the laptop to display. You can use here, either you can use a microphone, as I say, or anything that could display the audio sound. So now it's connected to the computer. One channel is connected to the computer, and the other one will be connected to the other external device. Now this time too, I use the computer because I try to find if I can find microphone, but this time I can't get it on the time. And then my speaker will be connected to the one of those channels right here. Then the power is on. Speaker. Sorry. Just give me a second here. Can you guys see? Why? Sorry for that. So what I'm trying to show, if you can see the LEDs here, they are being displayed. They are showing the frequency.
Yeah, we can see your LEDs.
So then,
can we get some sound? However, we don't hear the music.
Increase.
Cedric, we can't hear the music to correspond with the LEDs there.
Sorry, just give me a second. Sorry, what was that again?
We don't hear anything.
We don't hear anything. We just see the LEDs blinking, but there's no associated sound.
Okay, sorry, just give me a second here. Sorry about that. Let me try to change the sorry. Let me try to change.
Time improves him. Like certain varieties of artisanal cheese, Joe Biden is meant to be aged. And this gets sharper and more.
Sorry, just give me a second.
The next campaign will be even tastier. have you decided whether you are going to run for re-election in 2024? You haven't set up a re-election campaign yet, as your predecessor had at this time.
I'm going to take the other device so that I can plug it, please. Okay, sorry. So now I'm going to use this phone.
Now, we weren't in the room when Joe Biden said that, but according to those who
I'm going to use the phone. You can pretty much use the however what you can use to display your output. So here, what I'm going to demonstrate, as I mentioned at the beginning, it's if you have basically that's this for the DJ. Like if you want to if you want to talk and display and play the music, that's pretty much what I'm going to try. I'm going to use one device where we play the audio, and the other one use the voice, and the other one that I will use to display the music, the music basically. So for this I'm going to use the phone, which will play the music, and the other computer to display I choose randomly the speech, but I would just to show you how it operates, if you can still use it for different for the multiple inputs. So that's what I was trying to show you. Just give me a second here. Waiting all my life to live when I've only been dreaming. You love when I've only been stealing. Can't let time keep passing me by. Run down what I've always been chasing. Rock out everything I've been facing. I don't know if you can see anything. Can you guys see anything?
The bottom, the green LEDs blink once in a while there.
Yes.
Color organ isn't doing much, but we can hear your music.
Yeah, let me try it with the other device and see if that's better, probably, so that I can try. Just give me sorry about that. Sorry about that. Sorry for those little noises there. Sorry. Yeah. So
we have lights.
Yeah. Now I can increase the volume. Do you guys hear any change?
Don't hear any music.
Can you hear any change? I'm trying to increase and
oh, there was something there.
Yeah.
Okay.
Yeah. So, pretty much that's what I would like to show you. To show you how it operates.
Did you want to show us something about multiple inputs?
Yeah, sure. For some point, okay.
Not that America, we're gonna get a lot done. A lot. Of course, we'll get a lot more done.
Cedric, I think you had 5 minutes there to demonstrate there, so I think at this point we're going to cut the demonstration short. Okay, and we'll proceed to the question period. All right.
Yeah, not a problem.
Okay. So, can you bring up your schematic for a second, please?
Yeah, let me try to share my screen at a point. Yeah, schematic. Okay. Yep.
Okay, there you go. Okay, I've got a few questions, but the first question I have, well, it's a two-part question. Number one, so you used this schematic to build the PCB board, did you?
Yeah.
Yeah, okay. So, therefore, can you explain to me in zone 4A how that little tidbit of circuit works?
Zone
4A, the power input section there. It says power input.
Yeah.
Can you tell me what is going to happen when S1 is closed? S1.
Oh, switch?
Yeah, so switch S1, when you close that switch, what's
Yeah.
going to happen to your circuit?
To my circuit on the LEDs, you won't see anything.
Yeah, that's true. You won't see anything.
Because
What
like
happens
that's
when
where,
S1 is closed?
yeah, because like the switch is used to allow. It's like somewhere because you don't have to disconnect the wires. So instead of
No, listen to me. In that circuit, in that little portion of the circuit there, I want you to imagine S1 closed.
Yeah.
And I want you to tell me what's going to happen in that section of the circuit. Don't tell me what you expect it to do. Tell me what it does.
When it's closed?
Once S1 is closed, yes. What is connected?
So it would be like it would be connected.
No, don't go over there in that portion of the circuit in the middle there. If S1 was closed,
yes.
What is connected together?
It's the whole circuit.
What?
It's the circuit which allow the current to flow. I'm not sure if I'm getting the question.
So where will the current flow? Show me from your source, where will the current flow? If S1 is closed, where will the current flow?
So the direction of the current?
Show me where the current would flow.
It will flow this way, like
Where you're going all over the place there. Show me which wire, where would it go?
Yeah. So you see like point 1 and point 2?
Yes.
So then the current will flow going to that way to supply.
No. So where's the current coming from?
It's coming from the power, the power jack.
Okay, and then when S1 is closed,
then the current will flow this way.
Yes, and go where? No, keep your arrow on that wire.
Yeah, I know what you're trying to say. Yeah.
What am I trying to say? You haven't answered my question. What am I trying to say? I'm not trying to say anything. I want you to say something. The current flows there, and where does it go?
Yeah, so for this time, it's kind of closed. So yeah, I never think about that one before. Sorry.
So what happens?
Now,
where does the current go? Where does the current go?
It's shorted, so it would go back.
There, well, it wouldn't go back. It would short your power supply.
Yeah.
Right? So your circuit wouldn't work. If this is how it was wired, it would not work. Your ground, when you close your switch, your power and your ground would be shorted, and therefore nothing would have any other current flowing to it. Plus, you would hopefully your supply has a fuse or a current limiter.
Yeah,
right. So that is electrically wrong, right?
Yeah, I never think down before. Sorry, I didn't see that. Yeah, sorry about that. Yeah.
All right.
That's right.
Can we add to that too?
Sure.
Can we add to that same topic?
Sure, go ahead.
Let's say that you fixed that problem in your schematic. What's the next problem? Because I can't figure out how your power input circuit feeds the rest of the circuit.
Yeah.
Even if there wasn't a short to ground. Can you explain that?
So you trying to mean like where I should connect that one so that I can get the flow of the current into my circuit, or
well, let's imagine S1. Let's imagine S1's no longer in the circuit. You removed S1, so it no longer shorts.
Yes.
The current comes in from your power source, right? And where does it go?
So this time, as you see, that
no. Where does it go at that in that circuit?
So it will flow up there this way.
Okay. To what? Which node there?
What's to which node?
No. Yeah. Which node is that? You said it goes up there. What's that called?
That would be where it's like a positive side, because
what's it called? What did you label it?
9 volts.
Okay, and then where does it go? That's what you're alluding to, right, Mr. Broad?
Yep. Yes.
Where does it go?
It was supposed to go on those one says switch.
Really? Because that's called switch. Yeah, that's called switch. It's not called 9 volts.
But on this time, I labeled them switch because that's the switch I was talking about right here.
How would we know that?
How would we know? Yeah.
But better yet, how would your PCB layout package know that?
Yes, which is critically worse.
Yeah, that's maybe the labeling problem that I had. I was supposed to know.
I'm just questioning how your PCB ever got to work based on this schematic.
Yeah, that's definitely a question that comes to mind.
I mean, just here we found 2 critical faults.
Yeah. And because pretty much basically I used that one. I don't know how maybe I can try to show the one I used, but it's pretty much the same thing.
Well, I don't think so, because your PCB wouldn't work if it was the same thing.
Maybe there's something I will consider and then maybe try.
It's too late to consider. It's too late to consider. You have a board made.
Can I sneak a question in here too?
Yeah, by all means.
On your schematic.
Yes.
How many output channels do you have?
Output channels, I have 4.
How many output channels do you have on your project?
There are 4. So I don't know if you can see them.
There are 4 output?
Yep. Right here. Can you see?
Clear from your demo. No, well, I don't see it, but I'll take your word for it.
But are they really 4 output channels or just 4 output jacks?
Yeah, they're 4 output jacks, but they act like if you connect the speaker to this jack, to this output here, you will get a single from whatever how many input you connect to that one at the beginning.
So your input channel 3 does come out on an output channel 3?
Yes, and I can demonstrate.
And you have, we won't ask you to do that, and you have volume control over it?
Yeah.
Individually?
The only problem which I had, that one before, it's when they're all connected, like all 4 inputs are connected. So I can't get any control on those on the potentiometer right here. Then that's why I try to open one of the potentiometer so that I can still have those 3.
First of all, it's not a potentiometer; it's a rheostat under that configuration. Okay, and all your outputs are basically tied together. They're all shorted together.
Yes, that's the problem I mentioned. Like I found when I was doing my project.
Your outputs are all tied together.
So you don't have 4 output channels.
So you don't have 4 output channels.
The reason why I did that way, it's because you still need like a one single output. So how about like if I have like multiple speakers, so that I can connect one speaker on one channel and the other one on the other channel, so that I can still get the same like
but you're gonna be placing speakers in parallel. Okay, you're gonna be placing speakers in parallel, and that's going to vary the load on these amplifiers. Okay. I guess my next question based on this is, what's special about these amplifiers? What's special about the what is it? The LM 2900? Is it? No, 3900.
Yeah, sure. Those ones they are trying to receive the input signals and to transfer them. But
no, what's special?
Also it has to magnify.
No, what's special about that particular LM 2900? That's not the typical symbol for an op amp, and that's intentional. What's different between this symbol for an op amp and your typical op amp symbol?
The symbol?
Yeah. What's different? When you draw op amps in class, when you were shown op amps, was it the same symbol you used?
No, it won't be the same.
Why not?
Probably I use that one because that's the one I can find in like where I design my PCB.
Don't say that. I don't want to hear that. That symbol is the proper symbol for that op amp, because that op amp is a particular type of op amp. Did you look at the specification sheet?
Yeah, I can. I don't know if I can show it to you too, like in order to show you. So it would be like a one single with, because
that's not what. There is this particular op amp has a configuration to it. Okay, it's not like your typical op amps you saw in class. Okay, it's actually another type of op amp, and I'm asking you if you looked into whether that little symbol there is different for a reason. The little current source there. See, there's a current source there. Okay, it's like that for a reason. Do you know what that represents or what it means, or?
Not really, not that one.
No, so it never struck you to say, that's a different symbol. Maybe I should go look this up.
Because I thought that, because I found like the same thing that I was looking for in Ego. That's why I did try to think. Yeah.
Again, we don't, and there seems to be that belief here that whatever the drawing package is, let me just toss it in there, and who cares if the symbol is right or wrong or correct or incorrect, or if it's different, it doesn't mean anything. For example, I'll tell you right now, your power input symbol for your jack is the wrong symbol. It's the wrong symbol for that. So the same thing with these op amps. That symbol is the correct symbol for the type of op amp that's being used, but you're telling me you didn't, it means nothing to you. Okay, an LM2900 and an LM3900, which I can't seem to tell off of. You used the 3900. They're what are called Norton amplifiers. They are current differentiating amplifiers.
Yeah, they are.
They are. Why didn't you just say that a minute ago when I asked you about it?
Or maybe I didn't get basically what the question.
Okay, so what does a Norton amplifier do?
To amplify.
Don't they all amplify? Op amps are amplifiers by nature. What does a Norton amplifier do that a regular amplifier doesn't do?
They do amplify the signals. They're from the
all amplifiers amplify signals. Yes. What does a Norton amplifier do specifically? Okay, well, That's maybe, I think maybe we've reached the limit for that. Does anybody else have any other questions?
I had a question. It was in regards to the high pass filter, medium pass filter, and low pass filter. What is the frequency range for those three different filters?
For the high, sorry, let me start maybe from the. I didn't do I was planning to do the test for those to see basically practically what it is. But for the low, it will be between 60 and 100. So for the medium, it will be around 200 or 150 to 500, 500. I'm talking about the hertz. And the high would be 55 to up, or maybe the more than 1,000, sorry, hertz.
And what sets those frequencies? Which component sets those frequencies? Because you're giving me numbers.
That's the transistor. This transistor 2N39006.
No, absolutely not. Absolutely not. What sets? If I want to change those frequency values, you're telling me I have to change the transistors?
No. They are based on the input you are getting from.
No. Again, my question is, if I wanted the red LEDs to light up at a different frequency instead of whatever frequency you stated, which components would I need to change for that to happen?
It would be the knob, maybe to the volume, I can say.
No, volume controls amplitude across the board.
The reason why I'm saying this, it's because where you will get your external, right? So if you see on these LEDs, they are kind of high, and you want to maybe to minimize, so you will try to maybe to reduce using the volume for the.
No, I want a different frequency. I want to redesign, and I want a different frequency. I don't want the highs to turn on at 1,000. I want them to turn on at 10,000. What would I need to change component-wise for that to happen?
It would be that transistor there.
No, it wouldn't. No. Okay. I would be looking at C2R6. What else do you have here? C4R14, which, by the way, your schematic is much better laid out than what you provided to us. C3 and R16 would be the other components. You'll be changing the resistor capacitor combinations because they form a feedback filter in your transistor amplifiers there.
The one I provide to you guys, it was connected to the collector there, so that's why.
Well, that's fine. I don't mind that you provide us with a different version. It's clearly identified. I'm just saying the one you provided us is very messy compared to the one you have there, although yours is a bit messy too. But the one that I have in front of me here is really almost illegible at some points. Okay. Can you talk about diode D1?
D1, that when there is a short current occur in a circuit, because that's where this transistor, that one. So this we try to protect.
What would cause a short? Which device would short?
The device could short. It will be maybe should be caused by, if you see the way disconnection right there, and for some point it connects with the ground.
Well, why don't we protect IC1 from shorting too? Why don't you have diode protections there?
The main reason it was about if the input those signals I'm getting from here.
How does that cause a short? I think that's not a protection diode. I think you need to look into that too. Okay. All right. I think we've exceeded our time allotment. So, thank you, Cedric.
Thank you so much.
Okay. I would just also mention that probably your project would work a little better for yourself if you put knobs on the rheostats. All right, that should be something on your finish that you should order knobs. They're cheap. They're available. All right. Okay. Thank you.
Thank you so much.
We're going to take a 10-minute break, come back at 11:30, and I don't have my schedule in front of me.
I would agree.
It's Hirocell.
It's going to be Hirocell. So Hirocell will show us his beverage container counter. All right. So thank you. We'll see you in 10 minutes. All right, we're back, and I believe we're ready to go. So today is going by pretty quickly. We're already on our fourth presentation, which is Mr. Hirosel Seidel, and he's going to talk to us about his beverage container counter. Sorry, I got lost there. So he's going to talk to us about his beverage container counter. Mr. Seidel, are you ready?
Hello, can you hear me?
Yes, I can.
So I'll just have you share my screen here.
All right, so the floor is yours.
So, good morning, everybody. I hope you are all doing well today. And before I start, let me ask you all a question. So, have you ever wondered what happens to the plastic containers or the plastic balls that we throw in our bin? So, some of us might think it will be used again as a ball or perhaps a fiber, but it is recycled for a thermoform and many more. So, many of us used to drink on this beverage container, whether it is a plastic balls, cans, or a Tetra Pak. And we throw it on our garbage bin, and we can fill those bins, I think, in a week or two. So this leads me to the idea of making this project the beverage container counter. So I am Hirosel Seidel, an NBCC senior student an electronics industrial controls option with Mr. Broad as my technical advisor. And this is my SVL final presentation, an overview of the beverage container counter. And today, I will discuss about the purpose of this project, the functional overview, technical description, some tests, and finally, the project demonstration. So the purpose of this project is, as its name says, it is a beverage container counter. So mainly this device counts beverage containers. So it can count plastic balls, aluminum, a Tetra Pak, as long as the sensor could detect it. And in addition, upon using this project, people will have to segregate and collect their garbages, so for it to be recycled. So not only that this project's purpose is to count balls, so it also encourages people to recycle, which will have a positive impact on our environment. So this is the functional overview of how the beverage container counter works, and this is my block wiring diagram. And as we can see in here, what we need first for this device to operate is, of course, a power supply. So we need a power supply to supply voltage in order for the current to flow in the entire circuitry of the device. The next thing that this device have is the sensor. The IR sensor has both a transmitter here and a receiver. So upon powering it up, the transmitter will start to transmit a signal, IR signal, and then that signal will go nowhere, not unless it detects an object, or in this case, a plastic ball or a can. So whenever it detects a can, that signal reflects back to the receiver, and then the receiver will gives an output and sends that output into our IC counter. And what I have installed here is the manual control also, because sometimes this sensor misses the count, whether it couldn't detect the plastic balls or the beverage containers, or it overcounts. We have here the manual control to adjust the counts. It can increase the count by 1, decrease the count by 1. And the third button here is to reset the count back to 0. So the counter here has some kind the manual control here has some kind of problem because it is a push button switch and it has some mechanical issues like a switch bounce. So to counter that from happening, I installed here the switch debounce circuit to make the output signal clean. So the clean signal will comes to the IC counter by the 7-segment decoder, and because it has already a decoder in it, it can be connected directly to our 7-segment display to show our output. And that's it, the basic functional overview of my project. And for the technical description, for the physical parts of this project, it has divided into 2 parts. So this project is the main circuitry, or the main circuit of the project is all in what do you call this? Is an enclosure. So they are all in the enclosure, and the enclosure here consists of the project, and then the enclosure is attached to the aluminum chute. The aluminum chute will the one be guiding the beverage container to the sensor to be counted. So my aluminum enclosure here and the main parts of the project are inside this box. So this is the dimension of my enclosure. It is 12.7 centimeter in length. The width will be 10.16 centimeter, and the height is 5.08 centimeter. And because all the major components will be placed in here, I made some modification. I built some holes in here for the display. This is for the switch, and these 3 are for the push buttons. On its left side, I drilled 2 holes for the power, and this one is where the sensor comes out. And then the aluminum chute. The aluminum chute here guides the beverage container to the sensor. So I designed it as a slide, which will glide down the beverage container, the sensor, and it is also a triangular in shape to guide all the beverage to the center where the sensor is located. And here is the actual chute made on this project. As you can see here on the box, here is the IR sensor. So the following section contains the technical details of how major component works in this project, and it will describe its functionality with respect to the beverage container counter. So here are the main components used in this project: the power supply, the counter with the decoder IC, the sensor, the Schmidt trigger, and the debounce circuit, and then the 7-segment display. So the power supply here uses an AC to DC power supply. The input signal of the power supply ranges from 100 to 240 volts AC with 0.18 amps. And it will convert that voltage and current into a DC to output a 5-volt DC with a 1.0 amps. So this is the power supply located on my schematic diagram. And as you can see in here, it powers up almost all of the major components of the circuit. The next thing I have here is the IR sensor. This is a proximity sensor, and that detects a nearby object. So it operates in a diffuse mode sensor. So because it is a diffuse mode, it has both the transmitter and the receiver. The transmitter here is an IR LED, and the receiver here is a photodiode. The photodiode here operates just like a switch because whenever or if doesn't detect any IR light on it, it has a very high resistance between its anode and cathode. So it doesn't let the current to flow in it. So but when it detects light, the resistance here drops and then the current is able to flow. So the basic principles of how some sensor works. So here is the diagram of how the IR sensor works. So upon powering it up, this IR LED will start transmitting IR signal. So that signal will go to nowhere continuously. But when it detects an object or a reflective surface, or in this case, plastic ball or a can, a beverage container, then that signal will reflect back to the photodiode receiver. And here is the output of the IR sensor. So upon powering it up, the signal goes here, but the photodiode receiver doesn't detect anything. And when I measure the output, it outputs some 4.98 volts or a signal high. But when I place an object, in this case my finger in here, it serves as a reflective surface that reflects the signal back to the photodiode, and then as you can see here, the LED lit, and then the output goes down from signal high to signal low because it is now 0.409 volts or almost close to a 0 volt. So on my circuit, this here is my IR sensor, and this shows how the IR sensor connected on my project. So when an IR sensor detects an object, it is connected here to a transistor which serves as a switch. And whenever the sensor detects anything, it goes signal low, and then all the sensor here is connected to the count up. The next thing I have here is the Schmidt trigger and the debound circuit. One problem I encountered in doing this project is debounds. Is switch bounds. Switch bounds happen when pressing a push button switch because whenever pressing a switch, it seems that the two metal parts of the switch should have made contact to each other. So ideally, these should be in contact in that instance. However, in reality, they don't. For a few milliseconds, the switch bounces, and instead of making contact, it separates, breaks the contact, and then in contact again, breaks the contact, and this happens a few milliseconds. So because of this switch bound problem causes a major problem to my project, because whenever a switch bounce happen, it sends many pulses, and then instead of just one press, we expect one count, but because of the switch bounce, we can see it in the counter that it counts the number of switch bounce as well. So to counter this phenomenon, or to remove this switch one problem, a switch debound circuit here has been made. And here is an example of the switch debound circuit. So upon closing the switch, the resistor here, or the signal, will be pulled down to here. And this, but the R1 will prevent the circuit to be shorted. And then whenever the switch is open, the voltage will flow to here. I'm charging up the capacitor. So this capacitor will take time to charge whenever it's open, because the charging time will there's a time for it to be fully charged. And so this is the charging time of that capacitor, and upon installing the Schmidt trigger flows out to the output, so it will have a cleaner output here. So this is how the Schmidt trigger solves this problem. On IC, or the counter IC, has only only has a single threshold. So when I check it on the data sheet, the threshold is around 3.9 volts. So whenever the signal goes up from 3.9 goes down lower than 3.9 volts, it will start a pulse. So if we do have a noisy signal in a single press, maybe multiple pulses will be generated, and therefore it will register multiple counts. And here is from the datasheet of the Schmidt inverter. As we can see here, the gray area, it has an upper and a lower threshold voltage. Because it has an upper and lower threshold voltage, we can expect a cleaner signal. And here is how the Schmidt inverter, Schmidt trigger, cleans our signal. Because whenever the signal goes up, it should be higher than the upper threshold, and it will begin to start a pulse only when the signal goes below the lower threshold voltage. So even we have a noisy signal, we can expect a cleaner output because of that Schmidt trigger. So here is the Schmidt trigger in my diagram, in my schematic. And all the Schmidt trigger here is connected, and this is the switch debound circuit capacitor to filter out or clean the signal, the ripples, and then fed to the Schmidt trigger, and then to the count up and count down. The next thing I have here is the IC counter. For the IC counter, I used here is the Textras instrumental CD4110B Symposium decade up down counter. So the main feature of this IC counter is it has a separate clock up and a separate clock down pins, pins 9 and pin 7. And this IC also have decoder and a driver in it, so we can connect it directly to the 7th segment display. So here is the main IC, and it's connected directly to the 7th segment display. So with this IC, it is also possible to cascade, because as you can see here, it has a borrow and a carry pin. So the borrow pin, the carry pin will be connected to the clock up pin of the next CD40110B, and then the pin 11, the bar pin, will be connected to the next clock down, or the pin 7 of the next IC. So as you can see here, this is how I cascaded my circuit. And because I cascade on multiple IC, and I can produce a multiple output, multiple digits here. I used 3 IC to produce a 3-digit output. And here is the truth table of the CD40110B. As we can see here, it only counts up or counts down whenever it detects a pulse from a low to high. So when the input signal goes from high to low, it starts to count up, but from low to high count up. But if the signal is from high to low, it doesn't change anything. And here it is the 7-segment display. Using this circuit, I use 3 of this to display a 3-digit. And here is the internal circuit diagram of this common cathode 7-segment display. Because it's the common cathode, all the cathodes here are connected together and connected to pins 3 and 8, which is connected to the ground. And these anode pins can be connected directly to the outputs of the CD40110B IC counter. So display are here, and as you can see here, it is connected directly to the CD40110 IC counter. And for the test, unfortunately, due to the COVID-19, because we do have a limited access to almost everything, the test is not yet completed. So an addendum will be added in my report for the following week for the test. And the best thing I can think of for the test of this counter is the accuracy of its count. Whether to test is if it is reliable enough to count plastic balls and containers. So the first test is to check the accuracy of the counter. So in this test, I will run, let's say 20 balls in the counter and then check whether it counts accurately. And I will run the test on multiple times. And the next test that I will be having in there is to test the buttons. Because one major problem I encountered in doing this project is the switch bounce. So testing the buttons will ensure me that the problem has been resolved. So that's why I choose to test the manual control button, the increment to decrement button. And to conclude, the beverage container counter here is a device that will count a beverages container, whether it is a plastic or an aluminum ball. So as long as the sensor is able to detect it, and whenever a miscount happens or the sensor doesn't seem to count the balls, it has an adjust button to increment by 1 or decrement by 1 to count. And also there's a reset button to set all back to 0. And as per the last completed project functionality assessment last May 21st, the minimum functionality for this project has been met, and the beverage container counter can count on beverage containers. And the buttons works just as well. So there's still a minor bugs in this project, Like for instance, sometimes the sensor misses the count and it overcounts. And as for my question earlier today, that what happens to the plastic balls that we throw in our bin, I will quote Emily Chung of the CBC News. She says that many balls aren't recycled at all. They end up in the world's landfill and, or worse, in the oceans. So consuming large quantity of these beverage containers leads us to polluting our environment. So taking into consideration the number of the count that we monitor or with the use of this counter, we know that we can be aware of the trashes that we throw in our garbage. So if we know the number, the challenge is on how to reduce the count. And so that little by little we can make this world a better place to live. And that's the end of my presentation. And for the project demonstration, can you see the device?
Yeah.
As you can see here, this is my beverage container counter. It has a reset button, a decrement, and an increment button. And what we do have here is the sensor over there. So whenever I run plastic container or plastic balls or a beverage container of the sensor, it will start to count. So we can adjust the count. If so ever the sensor misses the count, we can adjust the count by pressing an increment button here or a decrement button here. And there's a reset here to set the count back to 0. And that is my brief presentation, my brief demonstration of my project.
Okay, thank you, Purcell. What a good presentation, great demonstration. Does anybody want to start with some questions? I'll cede the floor to anybody that has questions.
I have a question actually. Or Don, you go ahead. If you have a question.
Thanks, Denis. Quick one. You introduced Schmidt triggers as a debound circuit, and I'm looking at the symbol on your schematic. What is the process employed by your debound circuits to what do you call it when you have a different voltage level switching up and down? What's the name for that process?
I'm sorry, Mr. Parker.
Sorry?
Hello.
Yes.
What was that again?
Okay, looking at your debounce circuits, your Schmidt triggers.
Yes.
I'm looking for what do you call the phenomenon that you're using? You've incorporated a component that switches, it goes to one state at one voltage level and returns to the original state at a different voltage level. What do you call that?
I'm really not sure about that phenomenon. However, the voltage comes from high to low. Is that what you mean?
That's what I'm talking about. You even got a symbol on your 74 HC14s that sort of depicts what it is I'm looking for.
Oh,
there's a loop shown. What is the name of that loop?
Hysteresis.
Thank you very much. That's it.
Nice.
Well, it kind of reflects on the same topic. Can you bring up your schematic here, Sal?
Sure.
I was just curious to know your count up push button circuit and IR sensor. The signal from that flows through 2 Schmidt triggers, but the countdown push button only goes through 1.
Oh, yeah.
What's the reasoning behind that?
As I mentioned earlier here, the sensor always gives us a high signal because of giving high signal, it will trigger when the sensor is triggered, it will give a low signal. So whenever it gives a high signal in here, and the first time I used just a one Schmidt trigger here, that high signal will be converted, because it is an inverter, it will convert it into a low signal. So because it is converted to a low signal will be fed in this counter. And because it is a low signal, for some reason, even though that the sensor here gives us a high signal, but it has a low output here, for some reason, the sensor seems to always be triggered. So the LED on the sensor always be a lighting, and then I couldn't press anything at all. So even though I installed here an up to counter that, or a voltage here to pull up the voltage, it doesn't work. So one thing to resolve that problem is to, instead of, I used to put another inverter in series for this high signal to be low and to be high again.
Okay, so it's basically, one of them is acting as an inverter essentially.
Yeah.
Is that okay?
Well, I'd like to follow up on that question because I'm a little confused here, as to, so the input of U4A expects what kind of input? What's the logic type of input? Is it TTL, CMOS?
4A, I think it is a CMOS.
So it's CMOS, so it expects a value of either a small zero range or some kind of higher voltage value. Is that correct?
I think it's expecting a value around of 5 volts.
Okay, well, either 5 volts or 0 volts. Is that not right?
Yes.
Okay, so because it's got to be one of those two conditions. So when transistor Q1 is conducting, okay, the input to that device is obviously roughly 5 volts, right? It'll be in the upper near 5 volts. When it isn't conducting, what will be the voltage on that pin?
I know, when it's not conducting, the voltage in this pin is around nearly 0 volts.
No, it's not. Absolutely not. Where would it get 0 volts?
It has some small voltage, however, it is close to 0 when it is not conducting.
Well, actually, it'll get its ground probably from the 10K here, R2, right?
Yes.
Which is acting as a pull down, okay?
Yes.
Right. Okay. So, so what makes Q1 conduct?
What makes Q1 conduct is this sensor.
Okay. Well, what condition on the base does it need to conduct?
I think this is going to provide some the.
Well, is it a high voltage? Is it a low voltage?
It's the high voltage here. If it is some current on the base.
So it's going to play. Yeah, it's going. So that'll make it conduct. Okay.
Yes.
So that would mean something is triggered. Something is in the chute. Is that it?
Yes, because it's already it gives some always high here. So this is always conducting, but whenever it detects an object, and this will gives us servos, then it will stop this transistor from conducting.
Yeah, I think that some of the problem you're having here is because you attach the output of the transistor on its emitter leg instead of on the collector leg. Okay, it makes it a non-inverting switch, but it also causes a bit of issues with the pulling things high versus pulling things low. All right. Mm-hmm. So I think if you had connected it on the on pin 1 there, the collector leg, this first of all, you probably wouldn't have needed that second inverter. Okay. And it might have, because it would have acted like an inverter anyways, and it might have worked better that way, right?
Okay.
I since we're on here, I'm just going to grab another question here, and then I'll leave everything else to everybody after. What in the top left-hand corner there, you have your power section, I'm assuming.
Yes.
What does the component with S and T represent?
Actually, this this symbol is just not this is just the closest thing that I found in a KiCad. I couldn't find anything for.
Why didn't you build your own symbol?
Yeah, because I couldn't draw it on KiCad.
Sure you can. I use KiCad a lot, and I draw my symbols all the time. All the time. That KiCad has very much the ability to do that. Okay. So why did you not pursue that? Okay, this doesn't represent anything near what you want as a symbol.
Yeah.
Okay. First of all, it's too big. First of all,
and it's so different.
And it's totally different. That's right. Exactly. All right. So again, you should have picked a proper symbol. This is, and you've used it in several of your drawings and so on. So it's very misleading. All right. Anyway, I'll leave that to. I'll leave the rest of the questions to anybody else that wants to pose a few.
Before we go too far away from the switch bounce topic, you, I'll quote you in your presentation, quote unquote, switches have some kind of problem, and you said that in relation to the switch bounce topic.
Yes.
Can you explain that further in this way? I want to know the problem that you're describing. Is this a defect? Like, are these defective switches? And if they are, why didn't you just let the your supplier know and get replacement ones? Because you went to great lengths here to actually correct for this switch bounce problem. So is that the problem you're talking about, or is it what is this problem you're talking about that you went to such great lengths to try to solve?
Yeah, I think the problem is I use a different kind of switch now, because when it is on the prototype mode, I use a smaller switch, and because of that, it is easily resolved by using this switch bound circuit. However, when I change the switches to a bigger one, it has some kind of issues. Sometimes it is an overcounting, or because of that.
So that leads me to believe that the physical size of the switch has something to do with it, but I don't think it does it?
I think because it is a bigger switch and it has a bigger switch bound, so I think that might be
do you really think that the physical size has anything to do with it?
I think.
What causes switch bounce, and what could you do instead of implementing all this debounce, which we had some electronic information from Mr. Metcalf there on what you could have done to change the electronics here and help solve some of this. But if it is truly a switch bounce issue, what could you have done to address that at the switch level itself?
Yes, I think if I used a bigger switch, I could have changed the resistor here and the capacitor here, because adjusting the capacitor here makes a bigger room for you can control a bigger ripple, and also
you keep saying a bigger switch. I can show you some nice big switches in our lab that don't have any bounce, or it's so small, so it's not noticeable to any of the circuitry that we normally use with those switches, and they're a very large switch, but they don't exhibit any bounce or negligible bounce. So I don't think the actual physical size of the switch really has anything to do with that. What are we talking about here? How could you resolve this switch bounce in the switch itself? What would you do?
For in the switch itself, you probably just check the switches if they are all the mechanical components there are good, or tighten the screws up.
Okay, so when you say good, what do you mean by that?
Probably some of the switch might be have some loose, or it is not fixed on the enclosure well enough. So it's just like
this bouncing. Like, what is actual switch bounce? What is it? Is it when you say you're saying that the switch isn't firmly attached to something, but is the switch physically moving what causes switch bounce?
The switch bounce causes whenever when you press the switch, we expect that two conducting metals should be attached to each other in that very instant. However, it doesn't. So when we press the switch for a few seconds or a few milliseconds, they are detaching and attaching. So that I think causes the switch bounce.
So that mechanical bouncing effect, that you described, actually causes electrical bounce, switch bounce, what you call it, right? So how do we resolve? Is there a way I can resolve that by, in the switch itself? What could I do?
Probably in the switches.
What could you do in your case to resolve that?
For me, in the switches, I would just make sure to tighten the switch and to reattach well to the enclosure to minimize the shaking, and then I will install here just like I did the switch bounce circuit.
Let's go this way. How much did you pay for your switches?
Let me check here.
Like each unit cost.
Each, I think they are around $3. Let me check for the parts list here. Option 10. Yeah, for the switches, they cost $2.72, around $3 each.
Okay, so in the automation and process control industry, and you've seen some of these switches in the lab, they're a large and a really heavy switch. Like you have to push quite hard on them. I'm just describing what they look like and what they feel like to use. Those switches are typically, I don't know, you could spend $80 on a switch, okay? So, and I'm not saying that you should do that for this project, but I'm just saying that the quality of the switch definitely has an impact on that, doesn't it? And usually you pay more for something that's quality, right? So anyway, I just thought we should have a discussion on that. And then maybe that if you had chosen the switch more carefully, maybe you could have resolved some of these issues without having to go to the bother of having the extra electronics. Just saying.
All right. I have one. Yeah, I do have one question. Could you bring up the slide with the IR sensor? You were explaining the IR sensor.
The IR sensor. Okay. Oh, the slide.
Well, whichever slide that you had the pictures of the when you were explaining how the IR sensor works.
This one.
I don't know. All I see is your technical description. There you go. Oh, you had it there. Kind of went away.
Some kind of a delay.
Sure, that one there will do. That will do. I just again, I'm not gonna. I'm gonna be very general here to all students here. Okay. I felt like, and I've seen this in the previous presentations, and I hope I don't see as much in the follow-up presentations. But many of you are playing the cut and paste game with the internet, based on assuming that if it's on the internet, I can use it. Okay. I'm going to be honest here, ask you an honest question here, Sal. Could you not have come up with a very similar drawing yourself that described maybe instead of a reflective surface, you could have described it showing a container or a can, and it would have been much more appropriate than this cut and paste job that really didn't fit 100% your use?
Yes, I did.
So why did you not do that?
I did this on this black wire.
Well, sure, you did it there. Beautiful. That's exactly. This is beautiful. Why didn't you expand on this drawing here? On the other drawing, you went and sourced the drawing from the internet that I'm not so sure you have rights to use, to be honest. Okay, and at that point it becomes plagiarism. Oh, the big P word, right? And that, again, the penalty for that for the college is, we can all go look it up in the academic ethics policies. But if you're working somewheres, it becomes a lot more serious financially and job and career wise and such. And again, I'm not pointing just at you. I feel like in the last day and a half, some people, I don't know if they have an original picture in their presentation for some people. Okay. And here's how I'm glad you showed me this picture here, the block diagram that actually has that very excellent demonstration of that the IR beam reflecting off the can. It even has, animation showing that. And I'm asking you, and I'm going to ask all the other students, why not do that for all the other ones? Okay. It's, again, and I've talked about this in SPL, and I don't know if it fell on deaf ears, but just because it's on the internet doesn't mean that you can use it in your presentations or in your reports and so on and so forth. Okay. So again, I'm not pointing you out. I'm just taking this time to say that to everyone, because it really is. I find this year it's a problem, and it's a problem that instructors may start looking into and applying the plagiarism rule on it. Okay, so you all know what that entails. Plagiarism is not just about reports; it's about any kind of documentation and communication. All right. So at least the sources are being cited, but it doesn't mean that, again, just because you cite something doesn't mean you necessarily can use it. Okay.
Okay.
All right. So anyways, again, not picking directly on you here, Sal. It's just I noticed that you had a lot of outsourced images there, and I kind of want to just take the time to do that. Okay. All right. We're going to stop there for today, unless there's any more questions. I don't know if the panel has more questions.
Actually, I had a quick question. Can you bring up the schematic again?
Sure.
Logic question here. So the outputs from your Schmidt triggers, they're going to U1 at the top, The input
Yes.
7 and 9 there, what's that little symbol signify? That little triangle there.
Yeah, I didn't try to think about that.
Go back a year, their digital logic. It just means that it's edge triggered, positive.
Oh
edge
yeah,
triggered.
positive edge trigger. I remember now.
There you go.
Thought I'd ask.
All right. So thank you, Hirosel. Great presentation. Great project. It worked well in the demonstration there. It's going to count a lot of cans. And we're going to break for lunch now. We'll be back at 1:30 for our follow-up presentation, which will be Lakan Patel, who will show us his analysis of time over current relays. All right, and we'll have 2 presentations this afternoon, so please come back and join us for that, and that'll complete day 2, and we'll move on from there. So if again, also I'd like to point out, if you are viewing from the stream and there are problems or issues, please let us know. You can contact me through the email that was sent out, and just let us know about any issues with the stream. We really would like to hear and get some feedback on that. It's the old adage of no news is good news, but it's also maybe no news is people are complaining. So we just want to know if it's one or the other. So anyways, thank you, and we'll see you guys at 1:30. Okay, we're back. Sorry about that. Just at the last minute there, Mr. Broad told me there was 30 seconds to go, and my credentials expired for my team session. So it almost like it was intentional. So just Murphy's Law, I guess. All right. So everybody had a good lunch, I hope, and we're ready to start once more. So again, we have 2 sessions this afternoon, and at that point we'll be done for today, and we'll start again tomorrow at 8:30. Again, I just want to remind everybody tomorrow when you are logging in to make sure that you use the YouTube link for the 3rd day, because the previous day links they don't expire, but they obviously contain the content of the previous day's presentations. So once again, this afternoon we are going to see an analysis project titled "Analysis of Time over Current Relay" by Lucan Patel. So I hope that you all enjoy this. Lucan, are you ready to go?
Yeah, can you hear me?
Yep. I'll just step aside here and let you do your presentation. How's that?
Yeah, can everybody see my screen right now?
Yeah, we see it.
Okay, just so good afternoon, everyone. Today I'm going to talk about my project, but before that, let's begin with some motivational speech. So first of all, in a technologist or in engineering, as an engineering life, there are always challenges that we all have to deal with in our day-to-day professional life. Today is pandemic, tomorrow is something else, who knows? So when I had to choose a project in December 2020, when this SPL begins, I was very confused because things might be happening in the past 6 months. This college may go to lockdown just like the last year. And in that situation, how am I supposed to complete my project? That was the biggest question. So I have decided to do something from work from home. Right now, it's basically the culture is going on in industries and everywhere. Basically in the IT and other industries, not in the electrical, but that's how I get the idea to make this project. So before we begin, ask these 3 questions as mentioned in this presentation. Suppose if you get a job after your graduation as a project manager, just assume you are a project manager and you have to design a power plant. How are you going to do that? What's the first step? Now think the second question. You made the plant, everything is good. You have to hire people and train them virtually. You cannot do in-class training because of pandemic. Second question, that's the question. How are you going to do that? Third question is related to entrepreneurship. Means you don't want to work for somebody. I don't like boss culture and something like that. And you want to start your own business. So how are you going to start your own business then? After you graduate. So I will take a 10 seconds of pause for that and just let you guys think about it. You will get all the answers at the end for sure. So this is the 10-second pause for all you guys. Just think about it. Okay, I hope you guys figure something out. So let's begin with my presentation. So first of all, in my presentation, there are 2 test cases that I'm going to demonstrate in a short period of time. That's going to show the overall plant system in the simulation form. So in the actual plant, the relay is look like this. This is the microcontroller based relay. We are using similar kind of relay in the MATLAB simulation software. As you can see, the system is healthy right now. So this green LED is glowing and this is the red LED. When breaker breaks the circuit, this is going to operate. And yeah, so that's what it looks like in the real-time power plant. But I will demonstrate the similar results. So let's begin with the overview. So first off, we will start with the introduction. What is MATLAB, why we are using that, and what are the things that I use to design my entire system. Then I will explain the block diagram and the concept drawing to make this project to deliver this project in the simpler way. Then there are 2 test cases that I would like to deliver. Then the conclusion, which answer all those 3 questions that was included in the first presentation, then references, and then question. So first of all, introduction. What is MATLAB student version? So it has a lot of other features, not just on the electrical side, also in the mechanical sides too. So in the library of this simulating software, there are lots of features involved. Basically, you just have to pick things and connect all together. So it's pick and connect strategy. There are coding involved, but in my test cases, I didn't use codes. But yes, you can do the coding also. Now, that's the simplest part of this project. The hardest part is configuration. After you connect everything, it is not necessary that you get your results. For that, you need to configure things. You need to change some numbers. You need to add things. You need to remove things, resimulate again and again and again. And then at the end, you get your scope. This is a trial and error method, I guess. So in which I used basically all the blocks that is required for the generation side. So as you can see, power system. So like generator block, transformer, load, fault. This is all the basic things that we use that generally industries use for the power generation. For the relay logic, I use digital elements such as SR flip-flops, counters, relational operators, and RMS converter. So basically, that's the explanation of my project in introduction manner. Now we will go to the first topic, which is our block diagram. So as you can see, this is the generator block. That's our secondary protection. It has to trip, otherwise things may go sideways. We will see how it works. This is the relay. That's the power generation. That's our power plant basically. It has its own protection system. This is the relay that is segment under test, which means there are relay logic involved behind this that I did test it before presenting my project on May 21st. So we have two relay logics today that I will explain. Then the fault condition is basically the natural fault condition, which is line to ground, double line to ground, triple line to ground faults. Then the load network, again, this is the load side of the system, which means it has relays of primary relays which protect loads from the overcurrent, and then the analysis scope. This analysis scope is the overall part of the project in which we can see which relay is tripping at what time. So just to make things clear, this is the scenario 1. So our first test case is based on scenario 1, in which relay choose not to operate. Means the reference value to trip the relay is way more higher, that it does not detect the fault because the fault value is lower than that. So relay does not operate. That means faulty system that leads to unbalanced grid, fault spread, system damage. That also leads to safety risks such as loss of life. People may die because of that, because that is dangerous, high fault without protection. Explosion happens, fire happens, all the basic things that requires the safety manners. For the scenario 2, I used two relays, definite time overcurrent relay and instantaneous overcurrent relay. Let me be very clear. Definite time overcurrent means relay with delay. It should operate after a certain delay, and instantaneous means it should operate instantaneously upon fault detections. So as you can see in the system, fault apply to the grids, relay detects and breaker trips. What is the benefits of those? It's a reliable system. Customer like it because customer is safe due to that. His house is not burning. Industries are safe because of this. Mitigate safety risk. All the safety risks that are mentioned in the above figure, these all are risks that can be mitigated by using this system. Matter of fact, in the real time, this is the system that everybody is using nowadays. Suitable for expansion. If you want to expand the system based on the simulation design, you can analyze. You can add things, you can analyze other things, and you can generate your own expansion model. And then you can decide if you want to start an actual commission or not. Outage-free system, highly efficient, all that thing. That's for the scenario 2. We will go to our simulation to demonstrate our first scenario. So as you can see, this is power generating station. This is the breaker to protect this station. This is the breaker to protect this oil factory. As you can see, this is my oil factory. And this is my fault. So at 0.5 second, fault is gonna inject to the system and it's gonna travel towards here and it's gonna destroy everything in between. So let's start the simulation.
I'm not sure we're seeing the right screen.
Yeah, just a second. I am sorry about that. Just too many screens open in my. Can anybody see now?
That's more like it.
Is it good now? Can anybody see?
Yes, we can see, Lakan.
Yeah, thank you. So this is the generating station. This relay is to protect the generating side of the system. And this relay is to protect the load side of the system. And my load here is the oil factory. So this is my oil factory, as you can see in the image. So let's begin our simulation. Let's see how it goes. So just to take a close look here at 0.5 second here, when it reaches to 0.5, this is going to be fault is going to inject to the system, and this meter, as you can see, this current is increasing to the somewhere here. It's going to deflect to somewhere there. Just to make things clear, I just reduce the simulation time so like everybody can see what's going on in the actual scenario. So system is still in the healthy condition. There are no fault in the system. This is generating, and this load is consuming the power. As you can see, this is the load current. Everything is healthy right now. There are no fault in the system. But at 0.5 here, as you can see, at 0.5 here, there should be something is going to be happen. See, fault injected in the system. See this deflection? So as you can see, this fault is continue to operate and relay is not operating. I just stop it here because I have time constraint for the presentation. So as you can see, at 0.5 second, fault current is injected on the system, and it still continues its journey towards destroying the generator. Is everybody can see these waveforms? Let me just yeah, so this is the fault waveform. As you can see, this cycle is going to be continue because relay is not going to trip. This is the faulty system. So this is my first analysis. Faulty system, relay does not operate. We already discussed the consequences of it in the concept drawing. Now I would like to present my second test case, which is protected system scenario 2.
Okay, we see it.
Yeah, so as can be seen from this system, there are 2 relays installed in this system. This relay does not operate, but these relays operate. This is my definite time over current relay. This is my zone 1, and this is my zone 2. Both of these zones connected to the same power generator, and both of these relays gonna trip as per their own characteristics. we will see the waveform. And basically, this is the picture of the zone 1. So this is my power plant. It's going to supply load via transmission line. This is the distribution transformer. That's right there. This is the load side protection system. And this is my power industry of 33 kV load. In the other hand, there is a bus 2 connected on in the same grid, which is supplying the load to the household. So the household is basically anything like a house or apartment or something. It should operate instantaneously because we don't want to burn our house because of this fault situation. And this fault is injected to the system from the zone 1. So zone 1 fault is going to proceed to zone 2 and it's going to proceed towards the generating end. So let's begin. Yeah, just like the last present, this is a little bit fast. I have to just change some time. So as can be seen in the regular health system, generator is supplying load to the oil industry and to the household. So these 3 below meters are instantaneous overcurrent relay primary current emitters, and the upper 3 is the definite time over current relay primary current emitters. So it's going to measure the primary current on the zone 1, and the instantaneous current is going to measure the primary current of zone 2. And at 0.5 seconds, something is going to happen. And in the actual industry, it looks like this. So this is the switchyard control panel room of the power industries, where engineers can see what's going on from their end to the other end where they are sending their power. So in between, if there is a trip, this is the place where engineers can see that something is going to be wrong and they can add preventing actions according to that. So this this demonstration helps in to virtually train employees when especially we have pandemic situation to deal with. So that is the application of this module. You can train people virtually without even showing them the actual thing due to COVID constraints. Yeah, fault injected into the system. As you can see, this relay trip, this breaker trip instantaneously. And this is the time delay time. So as you can see, fault injected into the system. This breaker trips instantaneously. That means our house is safe without lights, but it is still safe. At least it's not burning. And this is the relay for the industrial load. That is the finite time overcurrent relay. It's going to trip after 8 fault cycles. That means 0.17 seconds of delay. And when it's going to trip, this is going to be a rate because this is the relay. It's going to trip. The load side relay is not going to trip. The generating side relay is going to trip because if this relay is going to that's the coordination as a backup protection. So as you can see, this relay tripped and now our current is going back to 0 because there are no current in the system. Everything is safe now. I will stop there due to time constraints. And I will present my analysis, which is there. Here is. Can anybody see this analysis screen?
We see a system diagram.
Okay, just a second. So this is what happens in the system. This is my instantaneous relay that trips directly. This is my 8 fault cycle. As you can see, 1, 2, 3, 4, 5, 6, 7, and 8. 8.5, and that's done. That's where the trip. So this is my delay, and this is instantaneous, all connected to the same system. Now we will talk about relay logic diagram a little bit. So this block contains the relay logic. As you can see, input value is coming from here. It's going to convert into RMS value. This is the relational operator that check the condition. If A is less than B, then output is true. True means 1. If A is not less than B, output is false in this condition, or output is fault because our reference value is 20 kiloamps and fault value is 36 kiloamps, I guess, which is more than that. So this is going to send 0 to this counter, It's going to reset the counter and it's going to count 8 cycles. That's what I define in the inside the blocks. So it's going to count 8 cycles, and at 8 cycle, it's going to trip. How it's going to trip? It's going to send 8.5 to here. That is going to compare with this block, and this block is, this condition is true because 8.5 is greater than 8, and it's going to send 1 to S part of the SR flip-flop as per the truth table. As you can see the truth table, S is equal to 1, R is equal to 0. That means 0. At the end, we need 0 because it's going to trip the breaker only when breaker gets 0 from the input. So this 0 is going to be AND gate. So all the 3 combined inputs from the 3 flip-flops is going to cooperate. It's going to come to the OR gate. OR gate is going to OR the operation of all 3, means 0 plus 0 plus 0. That is equal to 0. And that's going to trip our breaker. 0, 0, 0, 0. So that's what basically it is. Now I will go back to my presentation and we will review the conclusions. So first of all, project managers can use this design to determine the end stage of their project. They can design efficient and reliable system, and then they can schedule labor, cost, time, everything as per their experience and as per the deadlines. So first thing they need to know is the end stage of the product. If you want to design a power system, you need to know what's going to happen once you design it before you start even putting things like labor and stuff like that in your plan. Second thing is student and employers. So as student can learn something out of box from this. I know nowadays everything is book, but this is something that they can use to learn something out of box. It can be used for training and development purpose in the companies. It can fulfill the COVID requirements. Like last year, we didn't get a chance to go to MacTech. This can be helpful because of COVID, we cannot go to the certain place where we are supposed to. So it's going to help in that way. Research scope, research and development companies research and development department can use this project to create improved design in their existing system. It can also resolve the customer complaints and all the other things that comes under their attention that needs to be troubleshoot. Young entrepreneurs, if you want to start a new business, technologies can work as a consultant. If I am a consultant, if you want to build something, you can give me something that, like you said, I want to build a 33 kV power system. I can give you these designs and you can review it, and that way you can see like what's going to happen at the end. And these are my references, and now I would like to take questions. Yeah, so that was the end of the presentation. Though just one more thing before, oh, it's time. Am I allowed to just play a simple short video? If I may.
Yep, go ahead.
I'm just requesting you. Thank you.
Yes, go ahead.
So this video represents how breaker trips in the actual power system and how it sounds and how it looks like. So that's the breaker tripping sound. That's the video I would like to play.
I don't think we're getting the audio.
You don't get the audio?
We didn't get the audio.
Anyway, I will just upload it. No, just a second. I will play again.
that, Don? You missed it.
Is it good now?
We heard it that time.
Sorry?
We heard it that time.
So that's good.
Yes, we heard it, Lakankumar.
Yeah, thank you. So questions?
Could you please put up your reference or your citation slide? It was rather quickly.
Yes.
Okay.
Does this include all of the images that you used as well?
Yeah, I can code the images, but what the trouble is, when I did the slide design when it's gonna convert automatically, it's not showing the source. So see, like this. I just put the picture and then I just copy paste the picture and then I applied the slide design and that's where this source went somewhere else.
Yeah, you can override that though. Like the design ideas are just ideas that it gives you to make it look nicer.
Yeah. Yeah.
You still have to include the citing and sources. Otherwise, it's considered plagiarism because you're passing it off as if it's your image. And so in some cases on the references.
I did use those. I did cite the websites here. Like this is the first one. But for this two, I just I did cite. Then I did the design idea, and it went somewhere. So
yeah, you still have to cite it and source it. You can add text boxes in to do that.
Sorry about that.
All right. Well, we'll deal with that later, I guess. Just be aware of that. All right.
Yeah.
You gotta remember you're responsible for your work, your presentation. So if a software is trying to modify things, eliminate things, you need to make sure that what the requirements are there, right?
Yes, absolutely.
Yeah. So you go speeding down the highway at 100 miles an hour and the police stops you. I don't think blaming the car is going to cut it, right?
Well, and it actually states in NBCC's academic code of conduct.
I know, but as I said, it's just a slide design in which that thing goes.
Well, again, I think what we're saying is that's not really a valid excuse. Okay, so, anyways, well, let's go to some of your. Let's do some technical questions, and we'll if we have time, we can talk about this, or we'll talk about it later. How's that? Does anybody have some questions here for Lakan, Mr. Patel here?
So what was the project as a whole? It was an analysis on the simulation software, is that right?
Yeah, I did simulation on two relays, the definite time overcurrent relay and the instantaneous relay. You may have I already attached on the handout, like the drawing package that I uploaded.
If this was a simulation of relays, what were the relays? Were they physical relays, or it was just an ideal model?
Just an ideal relay with counters and using counters and SR flip-flops.
Okay.
I just designed some ideal format.
Okay, so you just recreated the theoretical functioning of the relays, and then you applied testing to show the reason why they should be used. Is that what it is?
Yes.
I think where you might have missed, a lot of us missed your point, Lakankumar. I'm going to make two observations here. One is that we spent a lot of time waiting for something to happen. And secondly, that would have been a great opportunity for you to give a little more background on just what it was we were seeing or what we should be expecting. For example, this is straight out of power system transmission analysis and protection.
Yes.
So those of the alternate energy students who studied that course, I'm sure, got more out of this than anybody who did not, right?
Yes.
So you could have perhaps spent more time describing we are talking transmission and distribution of power. And I'm going to specifically talk about the value of protection and the ways in which protection is implemented and the role of the overcurrent relay as a protection device. So that little bit of background would have added a lot to your presentation, I think.
Yeah, I get your point, but the thing is, when it's gonna cut that simulation time when people want to actually see that deflection of those arrows and stuff. So I was main focused on that objective, that the main analysis, the plant, the control model, that everybody can see that. So like, that's why I skipped certain things, but due to time constraint, as I said. But yes, that was my reply.
So I think I hear you disagreeing with me, which is fine. It's your problem.
I am agree with you, but
okay, but we did have time. While we were waiting for something to happen.
We had a lot of time.
Didn't know what we were waiting for.
Yeah, we had a lot of time. That's stated fact. So.
But everything worked as expected. We've covered the scenarios before. You've demonstrated it previously. Everything worked tickety-boo. But I think a lot of us were hoping for a little more understanding of what was going on.
Can you bring up your your block diagram? Sorry.
Yes, sure.
I just want to point out here that your block diagram, for me, again, I had never really seen what your project was about or anything, and I think your block diagram really did help you in trying to define what you were trying to do, okay, or you were doing, I guess, okay. For me, anyways, because I had a bit of a notion of what was going on utility side of things, okay. But I think that's just as again, I think the block diagram worked great for you. But then when you showed the Simulink models, although they try to be block diagram-ish, all right, they still aren't really, right? So that had a lot of people confused. And I'll tell you, to be honest, me too, I would have been confused had I not been a person that's already used Simulink, so I had a notion of how to read that, okay? So, again, I think, just wanted to put out here again, I don't know how critical it was for everybody to sit there and watch 2 or 3 simulations where the needles flip over, as opposed to you having concrete diagrams of what is happening, and then showing those waveforms at the end maybe too, right? As opposed to the trips. And so anyways, that's a judgment call, I guess, on whoever's going to present in that. But it did, I felt a little lost there for some bits too, and I consider myself a very knowledgeable man in some of this stuff. Okay, so just to give you a tip there, but the block diagram I found really worked well for you. Is just when you went and proceeded a little deeper, that got lost. So could you? I guess one thing that I'd like a little bit of clarification. So the two faults you were showing, where one was an unprotected fault and the other one was a protected fault. Is that what it was?
Basically, yes, but in the system form, which first is the unprotected system, second one is protected system.
Okay. And I guess, again, trying to get other people that don't necessarily have the background here. So when would both of these likely to be happening in the utilities plant outside plant? Like, maybe give us an example of each one where, if I'm sitting here looking at the thunderclouds coming over and the bad weather, when would I expect to see one versus another? And what form would it be under?
The first one, the failed one, that you will expect it to see when the bad weather is there, because that's a faulty system. Another one is also a faulty system, but it's gonna trip that fault, so you can see that also. So both the system you can compare with, you can combine with the bad weather.
Okay, but what I'm asking is, maybe tell us what would cause these faults. What are the causes of these faults?
It can be anything, like due to bad weather, fault happens due to conductor, break in the, like, broken conductors, or due to short circuit, due to like other reasons, like it can be like the distance between two conductors.
Yep.
If due to some reason the sag between them is not even, the sag distance is not even, and it's get closer, then it's going to be a short.
Sure. And why would that be?
Because the magnetic field, the conductor, when the supply passes to the conductor, it has magnetic field over it. So if two magnetic field interacts, it's going to create a short. That's why there is a distance between two conductors in the transmission line to distract those distract those fields from each other. If it interacts with each other, that's how fault creates in the system.
Is that the only reason it would do that?
There are other reasons, as I said. There could be external fault. That means the cloud, like the.
No. When you're talking about the conductor's proximity, what else would cause the shorting? Which actually we're talking about arcing, right? Not shorting, but arcing.
Yes. The other reason is surfaces of conductors. So as I said, the broken surfaces. Suppose this is the covered path and the top is broken, so that's going to leak it. That's going to leak current from it.
Yeah. Well. Oh yeah. I think if you're talking large utilities, they do not have insulated wire, do they?
Utilities do have no, the transmission line. I'm talking about the transmission line.
That's what I'm talking about too. Transmission lines don't usually have
insulated wires.
The big, large transmission towers are insulated, I think.
Yes.
No, I beg to differ. Even your 7200 volt on the top of a pole doesn't have.
They use ACSR conductor, I guess. And the ACSR conductor is like the conductor inside and in the center, and all the core part of the conductor, it has copper segments, and all the round side, the surfaces is like insulated with rubber or something, and in between.
I think
aluminum.
What's ACSR stand for? That'll tell you that you're wrong. If you knew what it stood for.
Yeah, I learned that.
You're forgetting. Besides that, what's installed in every single transmission tower that you wouldn't need if you had insulated wire?
Mm.
But all the towers are grounded, so.
Okay, so therefore, the reason
insulator, the black insulator in the connections, the plates, mica plates.
Yeah, that's right. There's an insulator installed at every tower for every cable that's connected to the tower, right? It's not connected directly to the tower, else it's short to ground. And the reason that is because the cables are
not insulated.
Non-insulated, that's right.
Okay, now it makes sense.
Yeah.
It's just for the structure of the conductor. I thought that.
So I guess my question was then, therefore, as the wires get closer together in between the towers, like you said, there's a distance there where, yes, there can be EM interaction there, but what else eventually fails? What's the insulator at that point? If it's not rubber, what insulates the two wires?
Non-conducting material, any non-conducting material.
So what is the non-conducting material? Between two bare wires, what would be the non-conducting material?
I guess air, but it
Air.
is conducting.
Air is the non-conductive material, but obviously, like any other dielectric material, any other insulator material, it has a breakdown voltage, right? And that breakdown voltage is based on distance also, right? It's breakdown voltage and distance. So when they get close enough together, the air breaks down, arcing, right? And then you do have an equivalent to a short or some kind of current discharge from one phase to another, which, again, your system would hopefully react to that and prevent any damage from occurring.
Yes.
All right. I think we're anybody else have any questions there? I think we're beyond the time limit, so we'll stop there. All right. Thank you. And we'll take our 10 minutes and start again at 2:30. And at that point, we'll have the final presentation of the day. All right. Thank you, everybody. Thank you, Lucan, for your presentation. It was good.
Thanks.
someone would kindly confirm that the audio is working.
It is working. That's good.
Thank you, guys.
Okay, we're back, I believe. So we're going to listen to our last presentation of the day, which involves Mr. Guillaume Vienno and a wireless PV system metrics monitor that he developed for a customer. So Guillaume, are you ready to go?
Yes. You can still see my screen and hear me well.
I have Mr. Broad up on the screen there. Hold on, maybe he needs to switch something. Oh,
I can see your screen there, Guillaume.
Okay, maybe it was just me then. So here you go.
Okay. Well, hello everybody. Thank you for the introduction, Mr. Metcalf. And for those of you who don't know, my name is Guillaume, and I am an electronics engineering technology student. And this is my senior project. So, as Mr. Metcalf said, this project first came around as a request from a friend of mine. So I'm going to name his name. His name is Zachary. He's probably listening right now. So hi, Zachary, if you're listening. And basically, he approached me last summer, actually, because he graduated from this program and knew I was going to go through this senior project, and said, hey, I have something. I have an idea for your senior project if you'd want to do it. So the situation is his dad owns a PV system. So that's in a non-technical term, it's a solar panel system for his home. And he wanted a way to monitor some of the metrics on his system. So this is I'm going to show you the design criteria that they wanted it for their system, and then tell you what I decided to do with that. So here we have the requested specifications. So his system runs on a 24 volt battery bank, but the voltage on a battery bank of this kind can go up and down. So he wants a system that can read between 24 and 28.5 volts on his battery pack. He also wants to know the current going into one of the inverters on his system, and this inverter powers his home. And he also wants the current to be measured in a non-interfering way, which means no obstruction of the wire going to the inverter. And I'm going to show you later how I achieved that. And then the monitoring device should be installed in a shipping container. This is what he has, outdoors, but not quite exposed to heavy rain or snow. But it's outdoor in the sense that it's not isolated, like temperature-wise, but it is still protected. So, but in an outdoor environment. And then the receiver should be 30 meters away, roughly, from the monitoring device, and that device can be indoors. So these are the design specifications that I adopted. It is everything that was requested and a little more. So as I said, the display battery bank voltage, the current going in the inverter, and then the receiver, I wanted to make it a handheld device. And then I wanted also to display the temperature of the system. So those are the design specifications that I based myself on to develop this project. Now for the functional block diagram, this is what resulted in those those criterias. So here I'm going to bring my mouse here. Actually, let me get a laser pointer right here. Okay, so that's probably a little easier to see here. So here we have the battery bank at the top of the monitoring device, the block diagram. And then it enters the cables go into the device and to an on-off switch, and from there in a fuse, and then the circuit itself. So I'm going to go into more details of this on the next coming slides, but there is 2 different voltage sources, and then the battery voltage also goes directly into one of the circuits, which again I'll get into more details later. And then here we have we use XBs for the wireless communication of the 2 devices. So these XP are communicating bidirectionally. And again, I'll get more details about that later. And then this is the receiving instrument. So like I said, the receiving instrument is a handheld device. It is contained in the case and is powered off here, as we can see, a wall power adapter. So this goes into an on-off switch, and then this is a 5-volt, as I'm going to mention, a 5-volt power switch that goes into some of the components here, and then a 3.3-volt regulator to go into the XP. Diving a little deeper into the details, pretty much what I was saying, a 5-volt wall adapter. So the microcontroller and the LCD both run off of 5 volts, so no need for extra power conversion here. But then here we have a 3.3 volt regulator because the XPs can only run on a 3.3 volt supply. And this is a switching regulator, as we'll see later. And also something that I sort of forgot to do in my block diagram here, but this logic level converter both needs the 3.3 volts here, and it also needs the 5 volts to switch those logic levels. Excuse me. So this is now the monitoring device, the second part of this. And as I said, we have a fuse and then going into the 2 power supplies. But let's talk about the actual sensors and measuring circuits here that we have to go to the XP. So the first one is the simple signal conditioning circuit that takes the battery voltage and attenuates it or conditions it to a signal that's readable by the XP. And here is the second measurement system here. This is the CSLA2EJ current sensor. And what's special about this sensor, as I said earlier, we want a non-interfering way to measure the current. So this is a Hall effect current sensor here. And the principles of a Hall effect is it's a semiconductor that varies its conductance, for a lack of a better term, according to a magnetic field. Now this sensor here has a ferromagnet surrounding the cable to measure the currents, and this ferromagnet has a slot at one point where the actual Hall effect sensor is placed. I'm sorry for the visuals ones out there. I should probably have put a picture in here of that to explain a little better, but I hope that makes sense. And anyways, so there's an output voltage from here that varies accordingly to the current that is going through the sensing loop of the device. Now, from here it goes into a signal conditioning circuit because the XP can't read what this outputs. And then here we have a TMP36 temperature sensor. This is a really easy to implement device. It's just a 3-pin semiconductor with a VCC, a power pin, a ground, and an output. And since it is powered off of a 3.3 volt regulator, the voltage cannot be in between anything else than 0 and 3.3 volts. So the XP can read it. I guess I should have mentioned before, this XP here reads voltages between 0 and its power, VCC, so which is 3.3 volts from this regulator. So anything below or above that can't be read by the analog to digital converter on the XB. So now let's dive a little deeper into basically what I just talked about. This is my schematic of the monitoring device. And the first thing we can see here is the jack designated CON1, and this goes to the fuse and then goes to the reference here, VBAT. So VBAT is the reference designator I chose to represent the battery voltage, pretty self-explanatory. And then here, or up top here, we have our 2 power supplies. So the first one here, this is a UA78L12, and it's a linear power supply that provides 12 volts. And these are our decoupling capacitors here, C1 and C2. And then here, a little more interesting, is our switching power supply, is a switching power supply. So this is the LM2594. And the way a switching power supply works is just like a switch. Without going into too much detail for now, the output is here, and it has what's called a switching interval. So it'll switch on and off the power with a certain duty cycle to generate the appropriate voltage. And I'll explain some of the components around here that makes this work as best as I can. So C3 here is what's called the C-in, the capacitor at the input. And the job of C3 is to smooth the voltage coming from the battery. Not that a battery voltage is unstable, but that's what it's there for. Here pin 5 is an on-off. It's just it is grounded to turn the device on. The ground pin here, and then this diode here. This is called the catch diode, I believe, and this is not your regular diode. This is called a Schottky diode, and it's the special characteristic of a Schottky diode is it switches. It has very fast switching speeds, which is required for the design of this this regulator here. And this is the inductor to store the current that comes out of here. It's like a capacitor that prevents a change in voltage. So here it prevents a change in current. Actually, coming back to this diode here, as I said, this is a switch, and so when the switch is on, voltage or current, sorry, will flow out of here and go into the inductor and at the output. But when the device is off, the inductor has current stored in it, so this provides a path for the current to flow out even when the device is off. Because if this was not here, when the switch would be off, there would be no path for current to flow. This provides a path that comes up from ground into the inductor at the output. So I hope that made sense. And C4 here is to smooth out the input. All right, now moving on to this section here. This is the current sensor signal conditioning circuit. So here we have two buffers coming in here. The first one being for what's called the offset voltage, which I'll get more into in a second. And this is the current sensor, the CSLA2EJ current sensor input going to the buffer here. And the reason why I put the buffers here is to make sure that the input or the output impedance here are both the same going into this differential amplifier here. And the job of this differential amplifier is to subtract a voltage. Now getting back to the CSLA2EJ current sensor, the way it outputs according to current is at 0 amps, it will output half of VCC, which means in this case it will output 6 volts at 0 amps. Now the XP obviously can't take 6 volts, so what I did here is I used this sort of calibration circuit here, if you want, that outputs 6 volts. And so the way a differential amplifier works is it subtracts 2 voltages, and so the voltage here is 6 volts, and here is also 6 volts at a 0 volts. 0 amps of current flowing in that sensor or through the sensor, which means if you subtract this from the sensor voltage, you'll get 0. And then here, let's say it is 7 volts because we have like 100 amps of current flowing. Then the output here will be 1 volt. I hope that makes sense. So this is the TMP36 temperature sensor, very self-explanatory, just a decoupling cap here and the output going to the XP. Now here is the battery voltage monitoring system. So this is just a voltage follower here, but what's important is this voltage divider here, and it is set so the output of the voltage divider is 1/10 of the input. So if I have 24 volts here, for example, 2.4 volts should be at this node right here, going into the non-inverting input of this this voltage follower. And it is adjusted through R6, which is a 10K potentiometer. And then this can create a resistance that is slightly above 10 kilo ohms. So that's it for the monitoring device. Now on to the receiver. The receiver has the exact same, with the same parts here, the same switching power supply. So I won't go over that a second time. And I'm going to start here to the microcontroller. So this is the heart of the project, and it goes to a few different places. Start off here, this is the programming port. Not much to say about this. It programs the microcontroller. This here is the LCD. So these connect the microcontroller with a few signals. Down below here on port C is the data bus of the LCD. So this is DB4 through 7. There is actually a DB0 through 3, but I'm running this in 4-bit mode, so I'm not using those 4 other ones. That's why they're not on the schematic. And yeah, they're connected on port C. Now port B here connects to the RS, which stands for register shift, the RW, which stands for read write, and the enable. And I will get more into this when I talk about the software of this program, the software of this device, sorry. Then now here, this is the I/O board. This connects to the user input, the buttons and the LEDs, which I'll show later. And here are the logic level converters that I was talking about. These are MOSFETs, eMOSFETs, that switch the logic signal of the logic level of the signal, sorry. So 5 volts on this side will give 3 volts on this side. And this is my XB here, the reset and decoupling cap. This is the I/O board I was talking about, so it's very, very simple circuit and a very simple board as well. It's just 4 buttons. And the reason why you don't see any pull-up resistors here is because I have the pull-up resistors activated internally to the microcontroller. And the LEDs here, I know we talked about this the same resistor for different LED colors. Actually, I guess you don't know this, but this is a red and this is a green LED. They are the same resistance value, and as a result of that, the current flowing through that LED has a less than a milliamp of difference. It's not much of a difference, but there still is one. It is not noticeable in daylight, but maybe in the dark. I actually have not checked that. So this is what the enclosure looks like for the monitoring device. I'm going to show you in person during the demonstration, but this is a weatherproof case, and it has a gasket, a rubber gasket surrounding the sort of the lip of the device here, and then the current sensor sits on the face of the device here, and this is the direction that the current should flow for it to be read. Here we have what are called glands. So these glands here hold the wire tight, and they also seal them. They seal the case so there's no leaking moisture coming into the device. And here's our antenna. This antenna is also weatherproofed, and this will literally be installed outdoors because obviously a shipping container is made of metal, and it would probably cause interference. So this is why this external antenna is here. Note that there is no external antenna on the following slide, which I'm going to show you, and this is the receiver. So the receiver here, we have our 5-volt power supply wall adapter that comes in from the top, our 4 buttons here, and our 2 LEDs and the LCD, and our switch. I guess there's not much to explain here. I want to add that this was probably the most difficult design to achieve. The height of this case is 30 millimeters, so it doesn't leave a whole lot of room to place an LCD, which was relatively thick, especially the bezel of the LCD, the onboard bezel of the LCD, and then getting these buttons and the switch it was pretty difficult to design and fit everything. Now I'm going to talk about my test. So as has been mentioned in earlier presentations, due to COVID-19, we've had scheduled delays. So the test will only be performed next week, but this is the test that I'm going to perform. The first one is the current display test. So this will test the accuracy and the precision of the current being displayed on here. And this is the test setup. You're going to see this in my demonstration as well. This is a battery pack that we have available in the alternate energy lab, and thanks to all the instructors who helped make this battery setup possible. And this is the battery tester. So here is basically a variable load with an ammeter, and I can see the actual current being drawn and then compared to what appears here. Now for my second test, it is an RSSI, which stands for a receive signal strength indication. And basically the way this test is performed is you have one device, a transmitting device in the center, and then a receiving device further and further away, and test the gain of the signal or sort of the losses in the signal the further you get away. So this gives a good indication of how far can the two devices communicate to each other. So now I'm gonna go over my software. I wish I would have included this in my presentation, but I'm gonna show you in VS Code what it looks like here. And it's not appearing. That's weird. Oh, right here. Okay. So I'm going to start off by saying, to be honest, this needs work. The software, it's able to achieve a certain amount of functionality, but not everything is here as I would want it. And I'm certainly going to be doing some more work in this code before selling the device to my friend Zachary here. So I'm going to start by going. I'm going to skip these defines here, but the most important part of what I have achieved up until now is the intermittent sampling of the XB. So the XB, the way the receiver gets its data from the XB is it will send a request to the XB to sample its ADC lines and return with its result. So the first function here sends a command, and I'm gonna scroll down here to where that function is here. Right here. So this is very simple send command. It just transmits a message through UART to the XB and sends these command bytes. And these command bytes, which appear here, are generated in XCTU, which is a software used to control XBs. And this basically the command that tells the XB sample your ADC lines and return with the results. So it goes through each byte in an array and sends those bytes to the XB. Now after that, it sends a command to the LCD to clear the display and then read the response. It reads the response, but it also updates the interface. This is part of the present state of the code that needs more work. So if we read the response here, the way it works is we have a buffer of 64 integers, and then we go through the response. So this is a while loop that says while the buffer index is less than 29, which is the length of the typical response, this gets executed, and this basically waits for a response on the UART. And then once a response is received, it gets out of this while loop and stores the response in the received buffer. And then after that, I honestly do not remember what this does. But the RX buffer will increment after going through this until it goes through the the entire length of the response. And then after that, it will go through the response because there's 29 different bytes in the response. It'll take the bytes that represent the ADC readings and store them in floats, which take a lot of memory. But this was the best way I could come up to store those responsive in a way that made sense to later display them. And then here we finally display these values. So without further ado, I am going to go to I'm going to do a demonstration here. And safety first, I'm going to be using or connecting something to a battery that has a lot of current. So obviously if this something was to go wrong, yeah, safety, you know, you have to protect yourself. So let me turn on the camera here to my monitoring device. All right. And before turning on the monitoring device, I'm going to turn on, or sorry, the receiving device, I'm going to turn on the monitor. And then here, you should see some readings on here. I don't know if this is clear. If someone could give me feedback if you can read what's on there.
Yeah, it looks good.
Great. Okay. So now I'm gonna plug connect the battery tester, and this is gonna turn on a fan because a lot of current or a lot of power has to be dissipated when I'm using this device, so it might make a little bit of noise. You have been warned. All right, so now I'm gonna increase the current going through the battery tester, and I'm gonna try to go for a 100 amps of current. So this should be about 100 amps here. Let's see, 120, maybe it's just me. Okay. Yeah, okay. See, so it reads about 100 amps on the battery tester right now. As you can see, because I haven't done the test yet, it is not quite accurately calibrated. But this is what's going on, and I want to show you now that I've shown you the interface. Oh, and I should mention these LEDs are part of the incomplete software, but these are alert or alarm LEDs, and the condition for this to turn on right now, the red LED, is the voltage has to be above 24 volts, but these should be further configured to the LED, the green LED should be configured for temperature, but it's not quite configured right now, but that's what they do. Anyways, so I want to show you more in depth the setup here that I have, and also show you the monitoring device. It's oh no, the device is connected. Just give me a second here. Oh, it's back. Great. So I'm going to try to show you as best as possible what's going on here. So this is the monitoring device. As you can see, these are the cable glands, the antenna, and this is the cable going through that sensor, as I was talking about earlier. So it really goes through what's called the sensing loop, and it is non-interfering, so it is electrically isolated from the device. And these are the batteries. But that's not really related, it's just the testing setup. Pretty interesting nonetheless. And that is it for my presentation here, and I am now ready to take some questions. Actually, before that, sorry, I'm just going to disconnect the battery tester. All right. I am ready to take some questions.
All right, Guillaume, great presentation, great demo there too. like you said, I think you probably need a little bit more work on it, but there's nothing wrong with that, right? That's what software is all about. It gives you flexibility in your design, right?
Yeah.
I'd just like to see, for starters, could you bring up your your block diagram? I guess your block diagram.
Okay, let's go to this one here.
Sure. I noticed at one point that you, when you were talking about the distribution of your voltage regulators and the outputs that they had to feed. And you kind of started, the one that struck me is you said the Mega 328 requires 5 volts, right?
Yeah, it's not completely true. You're right.
No. Could you elaborate on, do you know what the voltage range is for that?
I believe it can run between 2.7 and 5.5.
Yeah, it's actually 1.8, believe it or not.
1.8.
Yeah, I had to look it up.
That's
I didn't remember
good.
the range, but I knew it was much lower than. Yeah, so again, that's fine. I just when you said it needs 5 volts, I was like, no, it doesn't. But
No, you're right.
Same thing with your TMP 36. That runs about. I know it runs at about 2.5 to 5 volts, right? But again, if you need to feed into the XP, the XP is really the game spoiler in all this, because they don't run them higher than, I think, 3.6 or something like that. It's actually got a very narrow range of voltages, so it kind of forces you to have to do things. The other thing that struck me for power is, could you go to your schematic for, I guess, the monitoring device? You mentioned that the 7812 is a linear regulator, and then the 2594 is a switching regulator. Out of curiosity, since you were going to have already a switching regulator there, why didn't you just spend a few more bucks and make the 7812 a switching regulator too, to make the thing more efficient?
You're right. That is a very good point. There is honestly no particular reason, but I actually initially had two linear regulators. The 3.3 volts was also linear, and on the receiving device, they were both switching, the wall adapter and the microcontroller. 3.3 volts. So yeah, they were both linear supplies, and my train of thought was the analog circuitry would probably work better without any switching noise at all. So that was my first thought.
Definitely a consideration, by all means, but definitely a consideration.
Yeah. But the ironic thing about that is the reference has ripple. So because it's the 3.3 volts is rippling, right?
Yeah.
So it was a bit of a dilemma, honestly, and it sort of distracted me from the fact that I could maybe have both of them be switching. And actually, the reason why I switched to switching from linear for my 3.3 volt supply is it just the voltage drop just dissipated too much power. The case would have heated up, and it's supposed to be sealed. So that's why I made the switch, but I didn't do the switch to the 78L12. I don't really have a great reason for that, though.
All right, I was curious because you went out of your way to mention both and the technologies. I was like, well, that's kind of weird. He went one and the other, but again, there are considerations. A lot of times too. If you were going to go to version 2 of this or whatever, you have to, if you want to look at rippling and how to prevent that, we start talking about ferrite beads and more filtering at the outputs, right? So to try to minimize all those effects on your especially your instrumentation side of things, which kind of brings me just to this one last question for me. You mentioned, and I thought it was kind of clever the way you did it, to take the differential amplifier to make the output be within the range of the Zigbee input there. I forget what you quoted for a range there. So you kind of made an offset there, and you basically, you're assuming that it'll never go beyond whatever range that is. But in case it did go, is there some kind of protection you could have added here to prevent that from happening to your circuit?
Yeah, I did mess around with that. For me, there was two options, and the first one were Zener diodes that I thought could work, and I was breadboarding in a bit of a hurry, and I was trying to get the Zener diode to work, and I think something to do with the leakage current of a Zener diode made it so I would get a voltage drop across the resistor that goes before the Zener diode. Do you know what I mean?
Okay. Well,
because you need to limit the current, right?
That's right. So where would you have placed this Zener diode, and how would you have placed it?
Yeah. Okay. So after, let's look at at IC4.
Sure.
At the node between pin 6 and pin 5, the sensing and the output, I would have placed the current limiting resistor first of all to protect the Zener, and then after that, the Zener going to ground, which is what I remember from Zeners.
Oh, so you would have gone from that node through a resistor to through the Zener to ground. Yeah, it would have been something like that, and you can actually go the other way too, and have a maximum value too. It's very common to do that if you're doing any kind of automotive, marine, or avionics type of input signaling in that. You usually do clamp both ends. Or clip, I guess, at both ends to prevent that from happening, right? So there is, simple circuits out there to do that, but I can understand with the complexity of your circuit, maybe you were pressed for time. But that's good that you thought about that. That's definitely what I would have done too, is, don't depend on the two ICs always being able to prevent that fault from happening, right? Because good old Murphy's is around the corner waiting for you. So yeah, you would definitely want to look at in version 2, perhaps ensuring that your signal never either becomes too great or perhaps in the negative fault, right? That's the other problem, is going negative, right? That'll cause your XP to expire too, right? So, all right.
I also want to mention the other way that I thought would be great. This was worst for time because I would have had to order more components, but using if the differential amplifier was truly rail to rail, I could have fed it 3.3 volts, so it never would have went above that. That was my other option.
Yeah, that's right. That's another way of doing it. Yeah. Yeah, if it was, again, truly rail to rail. Yeah, that's good.
But finding a differential amplifier, unity gain, rail to rail, I did not find.
Oh,
I probably could have. I definitely could have, yeah. I just was pressed on time.
Yeah, I'm sure it exists.
Oh, yeah. Yeah, you're right.
All right.
You're right.
All right. Anyone else have questions? Sorry.
I'm trying to think of one.
I told him not to be too harsh earlier.
Well, that just primes him on. I have another one while we're waiting for somebody else. Could you go to your tests? I'm interested in one of your tests.
Is it the first or the second?
The second, the RSSI one, yeah, which is it's called a signal strength test, okay? I appreciate what you're trying to do with this test, which is trying to determine a functional range. Okay, the problem with this type of test, though, is whether there's obstacles in between, or the nature of the ground or nearby objects will alter those values significantly, and so will even the direction you're testing your antenna. So very often, instead of doing it like you want to do, what we do is we actually pick a distance that gives us a nice signal strength there in RSSI. And then what you want to do then is rotate your antenna 360 degrees, and at every 10 or 15 degrees, take a reading, okay, and then use a polar plot and read the draw a basically an antenna or a signal distribution plot, right? So based on the rotation. And what that tells you is it doesn't matter which direction you are, how far you are, or what the obstacles are. What it tells you is this is what you can expect depending on the direction you are from that actual antenna.
With no, in a line of sight in 360 degrees.
That's right. So what you do is you place yourself in a good signal strength. You got to be far field, right? You remember about far field, near field, right? In our course, you got to be far field, and you got to make sure that you've got a fairly average signal value there, whatever dB value you have, okay? And then what you want to do is you rotate the device under test, which would be the device that's at the center there. You want to rotate that, okay, and then you want to read the other device. You want to read the RSSI value, right, and convert that into dBs after. And basically, what you'll get, for example, if it was a straight up antenna that was ideal, what you would get is the same signal no matter which direction you're at. So you get a circle, right? Okay, but most antennas, because that's not true, because there's things that, the casing and all that, what you're going to get is a deviation from the circle, and those values that deviate end up being your true pattern, no matter what distance you would be at, as long as you can capture a signal. And that's much more useful to somebody than just having an RSSI value for distance, because those distance values, they vary a lot depending on the conditions, and you have to take them when they say this system works over 20 kilometers the line of sight and things like that. You got to take that with a big grain of salt, because it depends on the weather conditions, it depends on the ground in between, it depends if there's a truck going by, or all kinds of things like that. So that would be a better test for you based on what you have here. It's the same setup, except all you got to do is rotate your device under test, right, and plot your results differently.
The device in the middle.
That's right. You rotate that one. And you keep the other one at the same position all the time. It's easier to do that. Otherwise, what you have to do is go all the way around with the other device and travel a lot more distance. So it's just easier to place it at a distance and rotate the one in the middle, right?
And does this give like a better idea of in what direction to place the antenna?
That's right. It'll show you that you may have directions that are more favorable to point than others. Remember when we were designing the antenna field strength plots there in telecom? Right. So some of them were looked like two lobes on either side and things like that. So in your case, you probably not want something like that, or if you do have something like that, you want to be where the lobes are and not where the null points are, right?
Okay, yeah. I appreciate
no problem. No problem. All right, I'll leave this to somebody else there. I know we're getting close to the time there. Anybody else?
Quick one maybe on your switch mode regulator. Nice to see some power electronics here.
Yeah.
Now, you said that because of the voltage you're dropping here, you're going from 12 to 3.3. Now, did you measure high losses or calculate high losses in your regulator, or were you afraid? Did you expect high losses? Because, and I guess the question should include what current was coming out of your 2594. What was that feeding?
The current, I can only tell you, I did not measure the current going out. I apologize for that. I wish I had that data. But I can tell you that the current that was going into the 2594, which was around 40 milliamps.
40 milliamps. Times your voltage drop. Yeah. Were you experiencing heating of your regulator previously?
No.
Okay. Because I'm thinking I was looking at the output side, which is really only feeding an op amp, right? So not a lot of output current, but
are you talking about the linear regulator or the switching?
Your 2594.
Okay, well that only feeds the XB and the TMP36 on the monitor. The op amps are all powered by the linear regulator.
All right, so we could.
But the XB is what draws more current.
Oh, it does. Okay.
Yeah.
So it was more than just the op amp, the 412.
Yeah, that's good because a lot of those switching regulators actually have horrible efficiencies if the load is way too light, right?
Yeah, if the power dissipation and overheating is an issue, absolutely switching mode regulator. So it sounds like you did some math on it and you made a call and it was no doubt a good one. What do you call that configuration? That upper right hand corner of both your receiver and your monitor and your receiver.
A buck converter, is that the word you're looking for?
Thank you.
Okay, good.
Made an old man happy. Thank you. That's it for me.
I don't really have a question, but I do have a comment after reviewing your documents. The way you laid out the print for your code is pretty awful.
I'm sorry.
It could be formatted a little better. Well, it's just like a little snippet, but
yeah,
it's not using the full page, so just note to self.
I apologize for that.
Can I add to that
apologize
code?
for the lack of full flowchart.
Can I just add to the code? I noticed you used volatile variables. Can you do you know why you had to use volatile variables?
Yeah, a little bit about that. So my volatile variables, the ones that were used in the ISR, so that the only one actually that is used in the ISR is the timer overflow count.
Mm-hmm.
Now, this is what you have to do, from what I understand, with interrupt service routines. Your variables that are used within the service routine have to be volatile. I don't know why. I'm not sure. No.
Okay. Well, let me enlighten you. Anything where a variable could change unexpectedly. Okay. So if you have a hardware-based change, so if you have, like, for example, you're getting data from another hardware device that could be out of sync, and you're reading it on your input registers, and those could change in the middle of something, or in an interrupt service routine can happen at any time, right? Okay, so at that point you have to use volatile to tell the compiler that this value may change in the middle of a process, because what happens is it takes time to read registers or memory values, right? Especially at a bit level. So if the bits change while you're doing the read, it's going to be wrong. Okay, so you need to atomize. Yeah, you need to atomize your process, is what they call it, right? To be atomic. Okay, and that's what volatile helps you to do. Okay, so I was glad to see them there, and you'll notice all the volatiles are based on reading external values to registers and that, and I was glad to see that. I just wanted to know if you knew to use them, you just didn't know why, and that's fine.
Yeah, I want to ask you for the two last minutes, if possible, about those volatiles, because here they're all I use these, and I think this is the only way that it worked. This the floats and the variables that are read and converted from the monitor reading are volatile as well. Now,
I wouldn't have turned them to float right away. Okay, I would have kept them as integers, because they probably do come back integer anyways, don't they?
They do, and I convert them to float to get the decimal place, but I'm sure there's a better way to do this.
Yes, there is.
I just couldn't find.
You got to imagine where the decimal would be.
Yeah, exactly. No, I see what you mean, but I just didn't get to it.
All right, well, we'll talk about that later if you want to. All right.
Sure.
All right, thanks a lot, Guillaume. You did a really good job. Great demo, and it looks like a really good project. I think your customer will be quite satisfied with the product. All right.
Thank you.
I unfortunately didn't see in your presentation, you didn't show us a picture of your outsourced boards. Guillaume actually outsourced his boards, so you should have given us a picture of the final product when they're all soldered up. I would have loved to have seen that. So
they do look great.
They do, by all means. So, anyways, Guillaume did a very good job. All right. So, I'd like to thank everybody who presented today. You all did a great job. And I also like to thank everybody who took time out of their day to watch our presenters. And like I said, I learned a lot today. And I'm sure many of you did. This is it for today. We will be back tomorrow morning at 8:30. Using again, I'll just make sure I remind everybody that on your schedule there's a YouTube stream address for the third day. Please use that one for the Thursday. And besides that, we'll see everybody tomorrow. Thank you.
Bye, everyone.
Excuse me. The presentation will be done still through the Teams tomorrow, or it's gonna be YouTube somehow?
Pardon me?
Excuse me. The presentations are still scheduled to be done via Teams, right?
Yes. We stream to YouTube concurrently.
Okay. No, I understand that. It's just for watching.
Okay. Yeah.
Thank you. Sorry.